Okay, sir. We'll start, sir.
Yes.
Good morning, Reddy Garu. Good morning, sir. One of the person from Canada is also
Okay,
tomorrow's speaker, sir, Mr. M.V. Reddy. He serves in as nano-materials for energy materials, and he's in
Great.
Quebec, Canada, sir. Sir, Reddy
That's
Garu,
great.
Professor Sampath,
Okay, sir.
Hello.
Nice to meet you.
mentor,
Thank you, sir. Yeah.
my
Hello
mentor,
there.
my guide, is everything to me, right from my
Oh,
PhD.
very nice, sir.
So
So you might have known
he is
Sampath
there
Kumar,
to.
another Sampath Kumar from I think bioengineering.
Yeah, he is in biomaterials, sir.
Yeah,
Yeah.
yeah. Because
Yeah.
I know
Yeah.
him also, Sampath Kumar, another Sampath Kumar also.
Yeah. 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 Okay. Which university are you associated with, Professor?
Yeah, we are in presently we are a research institute. Maybe Concordia and McGill. Some of the research is like our lab is okay.
Okay. Okay. And which field are you working in?
I'm working in lithium batteries. Yeah, in fact, Varadaraju is also long back. We worked together when I was in
Okay.
Singapore. We worked with
Okay.
Varadaraju, some people from IIT Madras also long back. Yeah.
Professor Varadaraju has retired a couple of years back, and
Yes.
Professor Sampath Kumar has retired a few months back.
Oh, I didn't
But
know.
I think in some capacities they're associated with the institute even now. Yeah.
Oh, okay. Oh, I didn't know. I thought Sampath Kumar already retired. Okay. Okay.
Yeah,
So,
but no, he's still continuing
okay. Okay, sir.
into the next year.
Okay, sir. Right.
Yeah, yeah.
Okay, sir. Good morning, one and all. Today we are here for the inaugural function of AICTE sponsored 1 week faculty development program on recent advances in composites and nanomaterials. Today I have with me Professor V. Sampath, who is a professor in Department of Metallurgical and Materials Engineering, Indian Institute of Technology, Madras, Chennai. And it's my honor to have him with me on this platform. I welcome you, sir, on this and grace this occasion wholeheartedly. Uh, as you all know that today's world is looking at materials from all angles, right from aerospace to automobile, and even to, as Mr. Reddy was speaking, to batteries, where energy storage has taken a very big importance in today's world, especially in energy sector. So materials is playing a very important role. So we thought from our institute that it is very nice to have one of the faculty development program on composites and nanomaterials, so that this program can enhance the skills as well as the teaching aids for students, for faculty members from different institutes across India. And I'm happy to tell you that this program has got participants right from Kashmir to Kanyakumari. So I'm very happy that 132 participants have registered, and right from Kashmir to Kanyakumari, people across the country have registered this program. And I welcome all of you to this program. And on this occasion, I would like to introduce Dr. V. Sampath. Dr. Sampath obtained his BE honors from Regional College of Engineering, Trichy, and in rank he obtained a rank from that institute, and later on he obtained his ME and PhD degree from Indian Institute of Science, Bangalore, and he has got a lot of awards and honors to his credit. He was awarded Bharat Vikas Award in recognition of his excellence in scientific research by the Self-Reliance Institute, Orissa. He was awarded a Vidya Bharati Award by the Indian Institute of Metals for being one among the 4 students, and his name finds a regular place in Who is Who in Science and Engineering, published from USA. And he has got, to name, he has got a lot of awards and honors. If I keep on going, I have to list so many awards and honors which he has obtained. And right after his completion of his PhD, he is working as a professor in Indian Institute of Technology, Madras, and he has got over 30 years of teaching experience. And to his credit, he has published more than 150 papers in referred papers and journals and in conferences. And his research field include Mr. Gurjit Singh, can you please mute your mic? Mr. Gurjit Singh, can you please mute? And he was, as far as my knowledge goes, he was the first person to start the research in the field of shape memory alloys in India way back in 1990s. And a lot of PhDs have been obtained right from nickel titanium to copper-based shape memory alloys under his guidance. And I'm happy to tell you that I am also one of the recipient of a PhD degree under his guidance. And he has done a lot of research work, and he has got more than a few crores of rupees of a sponsored project, especially from Department of Science and Technology, Ministry of Human Resource, and today he is also handling a project internationally with along with Belgium as well as Soviet Union. So he has also conducted a lot of consultancies, and he has visited various universities abroad like Czechoslovakia, France, Philadelphia, Egypt, Turkey, to name a few. And he has been associated with the Indian Institute of Metals, Material Research Society of India, and Powder Metallurgy Association of India. He has authored also a book on smart materials and material science, and he is one of the reviewers for reputed journals like AICTE Materials, Smart Materials and Structures, Material Science and Engineering A, Journal of Alloys and Compounds. So on this occasion, I welcome you, sir, and I request you to tell a few words, and once the function is completed, then we'll hand over the session to you, sir. I welcome you, sir. Please take over from this, sir.
Thank you, Professor Raju, for the nice introduction. It's in fact a great honor for me to be speaking to you in the context of nanomaterials and composite materials. And so a very good morning to one and all. So first, let me give you a little introduction as far as this particular FD is concerned. And as far as this particular FD is concerned, it deals with materials, not only simply materials, but highly specialized materials such as nanomaterials and composite materials. Now, to give more importance to talk of materials, there is not a single human activity that does not involve the use of materials. We are so dependent on materials, not only for our survival, but also for our comfort and progress. Metals have become an integral part of our human life. And metals have also paved the way for our progress. And it is a quest for materials that has paved the way for the progress of human civilization. In fact, the history of civilization of mankind has been divided into the Stone Age, the Bronze Age, the Iron Age, etc. Now, presently, we are living in the Silicon Age or the Information Age. And metals have helped man to conquer space, time, and distance. In fact, society's progress is gauged by the nature of the materials used. Now, when it comes to the different materials, the classification of materials, we can divide materials using different criteria, such as whether there is any life in them or not. Accordingly, you have animate materials and inanimate materials. And we also use another criterion, and that is the use of properties and applications. So accordingly, we classify them based on the nature, properties, and applications. Now, based on nature, we classify them as metallic materials, ceramic materials, polymeric materials, and composite materials. We go in for composites when we wish to tailor-make certain unique properties that are not provided by these categories of materials alone. Yeah, there is a demand for newer materials. There are challenges to be met. There are new applications for which you need materials with newer properties, better properties, enhanced properties. And in order to meet the challenges of new applications, we're going for nanomaterials and composite materials. Materials at the nano level behave differently. They offer unusual physical, mechanical, and chemical properties. These subjects are therefore very interesting, and in fact, they deserve a deeper study. No wonder this FDP will, in fact, serve the purpose. And I believe this FDP will increase the horizon of your knowledge. And I want to take this opportunity to congratulate the coordinators, especially Professor Raju and his colleagues, for having chosen a very relevant, very timely topic for an FDP. I hope that the present lecture, as well as the lectures to come, will serve the purpose of meeting the needs of the faculty from different departments of the institute. I'm really glad that the participants come not only from the southern part of India, but from all over the country. So that speaks volumes for the importance of the subject, the relevance of the subject. So without taking much of your time, let me finish by saying that this course will be really useful, and I wish the organizers and as well as the participants a lot of success and a lot of benefit. I hope you'll gain a world of knowledge by attending this particular program on nanomaterials and composite materials. So thank you once again, and I wish you lots of success, and I hope the conference, the FDP will meet the intended purpose. Thank you once again.
Thank you, sir. Thank you very much, sir. On this occasion, I also welcome all the participants to this FDP who have joined late. Now I request Professor Bairegoda to deliver the vote of thanks. And sir, once the vote of thanks is finished, you can start your session, sir.
Okay.
Hello, good morning, everyone. This is Bairegoda, Mechanical Department, and I am giving vote of thanks for this inaugural function. It is my privilege to thank Dr. V. Sampath, Professor, Department of Metallurgical and Materials Engineering, Indian Institute of Technology, Madras, Chennai, for being the chief guest of this 5 days faculty development program on recent advances in composites and nanomaterials under Atal AICTE Training and Leadership Sponsorship. And also, I heartily thank Sri S. Mariswamy, Chairman of PVP Welfare Trust, for presiding over the inaugural session of this FTP. And I sincerely thank Sri A.R. Krishnamurthy, Managing Trustee and Honorable Secretary of PVP Welfare Trust, Dr. B.N. Umesh, Treasurer of PVP Welfare Trust, Sri P.L. Nanjundaswamy, Trustee of PVP Welfare Trust, Sri S. Shivamallu, Trustee of PVP Welfare Trust, and Dr. M. Mahadeva, Trustee of PVP Welfare Trust, for being the guest of honor for this FTP. I would like to thank Dr. Ambedkar Institute of Technology for giving platform to conduct this FTP, and also I thank Principal Dr. M. Meenakshi, Vice Principal Vijay Kumar MV, Dean Academic Anuradha KN for supporting in all aspects related to this FTP. Also, I will be falling in my duties if I do not thank our Chief Coordinator of this FTP, Dr. T.N. Raju, for following up the planning of this FTP right from the word go. I thank my colleagues, coordinators who have been the back support for several aspects of this FTP. Lastly, all the participants actively registered for this FTP are to be thanked for being in this FTP and this making it a success. Thank you.
Sir, over to you, sir. You can start sharing your screen.
Sure. Good morning once again. My name is Sampath and I'm a professor of Metallurgical and Materials Engineering at AICTE Madras. I've been working on shaping alloys for a couple of decades now. The subject is very interesting and very absorbing. So as far as the talk is concerned, I'm going to talk on shape memory alloys from different perspectives. That is the principles, mechanisms, and applications. Now, what are shape memory alloys? So these are basically alloys, that means metallic materials, and they have the unique property of memory. But then memory related to what? Memory relating to their initial shape, their original shape. Okay? And these are in fact novel materials. Now, when it comes to shape memory alloys, different terms are made use of to refer to shape memory alloys. For example, thermo-responsive materials. Why the name thermo-responsive materials? This is because on exposure to high temperature, they revert to the initial shape. They are called marmon alloys. Why the name marmon alloys? This word marmon can be divided into two, M-A-R, mar, and M-E-M, memory. So what does it mean? It means martensite memory. M-A-R stands for martensite and M-E-M stands for memory. In other words, the memory that these alloys have is related to the presence of martensite, or rather due to the occurrence of two transformations, that is austenite to martensite and martensite to austenite. And it is the reversibility of martensite that gives rise to the shape change. And these are also called memory metals because they have a memory pertaining to the initial shape, the original shape, and a shape before deformation. And they're also called smart metals. Now, there is a class of materials known as smart materials. What are these? Smart materials are those materials which respond to different environment, different stimulants. And that's why the name smart materials. And these are also called smart materials. In particular, they're called smart metals because they can respond to a change in temperature. They can respond to stress. And that's why the name smart metals. Now, when it comes to shape memory materials, most of them are metallic. That means shape memory alloys. But then, apart from metallic materials, there are also other materials which exhibit shape memory effect. For example, SMCs, the shape memory ceramics, then SMPs, shape memory polymers. The shape memory polymers are also known as smart gels. But then as you go from shape memory alloys to shape memory ceramics to shape memory polymers, the properties are different, especially the property of strain recovery. The strain recovery is much, much higher in the case of shape memory polymers as compared to the shape memory ceramics and shape memory alloys. Now, coming to the most important thing pertaining to shape memory alloys, they exhibit two unique properties, namely shape memory effect and superelastic effect. Now, shape memory effect is also known as thermal memory effect. Here, temperature plays a major role. And shape memory alloys also exhibit another unique property, and that is called superelastic effect. This is also known as mechanical memory effect, thermal memory effect, and mechanical memory effect. And shape memory alloys are used for a variety of applications. In some applications, shape memory effect is made use of. In certain other applications, superelastic effect is made use of. Now, to go into a formal definition of shape memory alloys, these are basically metallic materials that have the unique capability to revert to their initial or original shape when subjected to appropriate thermal procedure or stress cycling. So I like to emphasize the fact that it is temperature which can act as the stimulant, or the load or the stress which can act as the stimulant. So that is why we say that shape memory alloys exhibit the two unique properties of shape memory effect, that is temperature based, and superelastic effect, that is load based. Okay. And so if you look at the reasons as to why shape memory alloys exhibit shape memory effect and superelastic effect, it is attributed to the phase transformations which occur. They undergo phase transformations when subjected to appropriate thermal procedure or stress cycling. And it is a reversibility of the phase changes that is responsible for the phenomena. As I said earlier, these alloys undergo austenite to martensite and martensite to austenite transformations. So it is the reversibility of the phase changes that is responsible for the phenomenon. Now, coming to the history of shape memory alloys, the subject is not all that new, but then the subject is still fresh because a lot of research is still going on in the area of shape memory alloys. So there is a larger community of scientists working exclusively on shape memory alloys. And when it comes to applications, shape memory alloys are used from simple to very sophisticated applications. But then to trace the history of shape memory alloys, way back in the 1930s, a Swedish scientist by name A. Wallander worked on a copper gold alloy. In fact, he studied the pseudoelastic behavior of shape memory alloys. Subsequently, a number of scientists worked on different alloys such as copper, zinc, and so on. And it was in the 1960s a major breakthrough was achieved. And in fact, it was Bueller and his co-workers by name Wiley and others now who made a phenomenal contribution to the field of shape memory alloys. The alloys are many, but even though there are many alloys, it is basically the nickel titanium alloys which have been very popular. In fact, the initial work was carried out in the 1960s, but then even today, the nickel titanium alloys are so popular and they are used in many, many applications. Now coming to the principles of shape memory effect, so let us discuss the principle. So let me take an alloy, especially a shape memory alloy of the appropriate composition. Now, when it comes to any shape memory alloy, there are four different temperatures which are important. As I said earlier, it is the phase transformation or a couple of phase transformations which play a very major role in the reversibility of the shape change. Now, there are four different temperatures. These temperatures are also known as characteristic transformation temperatures. So what do you mean by characteristic transformation temperatures? That means these are chemistry dependent. These are composition dependent. If you change the composition, these temperatures will also change. And so the composition is very, very important. Now coming to the temperatures, so we use the letters M, the letter M to refer to martensite and letter A to refer to austenite. So there are two different phases that are formed in the case of shape memory alloys. And what about the letter subscripts S and F? S stands for start and F for finish. So you have martensite start and you have martensite finish. temperatures and your austenite start and your austenite finish temperatures. So initially, the alloy is heated to above its AF temperature. So that means the alloy will have 100% austenite. Above AF, the alloy will have 100% austenite in its composition. Now I start cooling the alloy from above AF. As I start cooling, no change takes place till I attain this particular temperature, known as MS temperature. When I reach this particular temperature, that is MS temperature, the austenite gets converted to martensite. It gets transformed to martensite. So that's only the beginning of the transformation, but then the transformation occurs over a range of temperatures. So this transformation keeps on occurring till I reach this particular temperature, MF, upon which the transformation is complete. That means when austenite is cooled, or to be more precise, when austenite is quenched, it undergoes the martensitic transformation over a range of temperatures, that is MS and MF. Now, as you can see, between MS and MF, you find that the amount of martensite changes over from 0% martensite to 100% martensite. Now, below MF, you have 100% martensite. So this is known as the forward transformation. This is known as the forward transformation. Now, coming to the reverse transformation, I start heating the alloy. Now I start heating the alloy, and the reverse transformation now should take place. Strictly speaking, the reverse transformation should trace the same path as the forward transformation. But in most cases, it is not so. Most of the alloys do not follow this particular trend. Most of the alloys show a gap, and that is known as hysteresis. To be more precise, it is known as thermal hysteresis. Now, as I start cooling the alloy, the reverse transformation takes place, and when I reach this particular temperature, known as the AS temperature, the martensite gets transformed to austenite. And as I continue to cool, more and more amount of martensite is austenite is formed, and at this particular temperature, AF, the transformation is complete. And at this temperature, I find 100% austenite. In other words, between AS and AF, 100% martensite is formed. That is, to start with, it's initially 0%, and at AF, when the transformation is complete, you have 100% austenite. So these are the transformations which are occurring. So these transformations are key to shape memory effect and also to superelastic effect. Now, coming to the shape of the stress strain curve, so now especially I like to throw more light on the hysteresis. Okay, so in some alloys, the width of the hysteresis loop is much larger. In some cases, it is much smaller. And so in fact, this gives you the clue as to the kind of applications they are to be applied or they are to be used. So in some applications, you need the thermohysteresis to be much, much smaller. In certain other applications, you like to have the loop to be much wider. When do you have a wider loop and when do you have a smaller loop? If you want to use the alloy for actuator applications, then you should go in for an alloy with a smaller hysteresis loop. On the other hand, if you like to use the alloy for damping applications, then you should use an alloy with a wider hysteresis loop. Coming to the composition of different shape memory alloys. So I would like to draw your attention to two important parameters. One, the transformation temperature and then the transformation hysteresis. So you know that when it comes to shape alloys, the 4 temperatures are important: AS, AF, MS, and MF. These are known as the characteristic transformation temperatures. Yeah, characteristic transformation temperatures. And so as you can see here, different alloys have different ranges. And depending upon the application, you can choose the range. Now, that's one thing. Secondly, hysteresis. So as you can see, in the case of indium titanium alloys, the hysteresis is only 4 degrees centigrade. In certain other cases, it can be much larger. In fact, in the case of iron-based alloys, the width is much, much larger. So let me move on to superelastic effect. So this is basically a high temperature phenomenon. This is also known as the mechanical memory effect. Okay, so this is basically a high temperature phenomenon. The metal is heated to the AF temperature. That means it will have austenite in its microstructure. And in the austenitic condition, the metal is loaded. And during loading, when it reaches a particular stress level, it undergoes a transformation. And this is called stress-induced transformation of austenite to martensite. So this curve actually shows 2 different plateaus. The upper one is called the upper plateau, and the lower one is known as the lower plateau. So during this phase, the austenite gets converted to martensite. Please note the unique shape of the stress strain curve, because during the entire transformation, the load is almost constant. So during this phase, austenite gets converted to martensite. Austenite gets converted to martensite, and a martensite so formed is called stress-induced martensite. And upon unloading, the reverse transformation takes place. And during which phase the martensite gets converted to austenite. Okay, and this hysteresis is called stress hysteresis. So please note that there are certain applications for which shape memory effect is made use of, and there are certain other devices which make use of the superelastic effect. Now, coming to the mechanism of shape memory effect. So we see these changes externally. So with the naked eye, we see the changes that are taking place, the changes in length, the changes in shape, etc. But then internally, many changes do take place. So let us trace the crystallographic changes that are responsible for shape memory effect. So let us take a shape memory alloy which has a specific composition and which can give rise to shape memory effect. And so this has a specific length and this has a specific shape. And now in the case of shape memory alloys, you come across 2 different phases. One is austenite and the other one is martensite. And the martensite in shape memory alloys is usually referred to by the Greek letter beta. But then in the case of conventional martensite, that is iron carbon martensite or martensite which occurs in iron-based alloys, it is referred to as the gamma phase. But in shape memory alloys, you use a different notation, namely beta. So the alloy is heated to above the AF temperature, and now it is quenched to below MF. It's not MS, but MF. And upon quenching, it gives rise to martensite. And so this martensite is also known as self-accommodating martensite. Please note that in the case of conventional iron carbon alloys, when martensite is formed, the metal undergoes cracking. or the metal undergoes a change in volume. So these are characteristics of the iron carbon martensite. But in the case of shape memory alloys, you find that the martensite that is formed does not give rise to any change in volume. Okay. And please note that, so the martensite that is formed shows plates. Also, these are also called variants. As you can see here, there are 4 different variants: A, B, C, and D. So these 4 variants are joined together at their interfaces. Once again, the variants A, B, C, and D are joined together at their boundaries, at their interfaces. When one is disturbed, the other ones are disturbed as well. Okay, so this, why the name self-accommodating martensite? The name comes from the fact that they accommodate themselves in such a way that the overall shape change is 0. The overall length change is 0. So you find that this has a specific length, and after transformation also the length remains the same. If at all there's a change in length, it is negligible. It's negligible. So that is the nature of the transformation that occurs in the case of shape memory alloys. And so these are twins. The variants are basically twins, A, B, C, and D. And they are interconnected at their interfaces. And as I said earlier, when one is affected, the other ones are affected as well. Now, I am deforming the martensite so formed. And it can so happen that among the 4 variants A, B, C, and D, the one variant which is favorably oriented along the stress direction. So this is the direction of stress application. And even though there are 4 variants, among the 4 variants, one variant is favorably oriented with the stress direction. So this grows at the expense of others. So among the 4 variants A, B, C, and D, A grows at the expense of B, C, and D. So as you start loading, unloading, as you continue loading, at the end of the loading process, at the end of stressing, only one particular variant will be left behind, and that will be A. And this particular variant, upon heating, will lead to the reversion to the earlier shape. And this is what is known as shape memory effect. So all this takes place at the crystal structure level. Now, shape memory alloys exhibit 2 different forms of shape memory effect. That is one-way shape memory effect and two-way shape memory effect. What is one-way shape memory effect? One-way shape memory effect refers to the alloy remembering only its high temperature shape. One second. In the case of one-way shape memory effect, the alloy remembers only its high temperature shape, that is shape in austenite. And there is another form of shape memory effect that's called two-way shape memory effect. Here it is. So two-way shape memory effect. So in the case of two-way shape memory effect, the alloy remembers both its high temperature shape and its low temperature shape. So look at this particular spring. So the spring is below its MF temperature, and upon heating, it expands. Upon heating to above AF temperature, it expands. So that is, the metal remembers both its low temperature shape and its high temperature shape. That is, it can remember its shape in austenite and its shape in martensite. So that is known as two-way shape memory effect. But one thing that is to be borne in mind, and that is most materials will exhibit only one-way shape memory effect unless and until trained. The material is to be trained to exhibit two-way shape memory effect. If the shape memory alloy is not trained, it will not exhibit two-way shape memory effect. Now, coming to the mechanism of shape memory effect, as I said earlier, what you see externally is pertaining to the macroscopic changes. Okay, so changes take place at different levels. That is, at the macro level, then at the micro level, then at the crystal structure level, then at the atomic level. So once again, changes do take place at different levels. At the macro level, then at the micro level, then at the crystal structure level, then at the atomic level. So, but what you see externally is only macro. Okay. So let us look at the mechanism of a shape memory effect. So this shows what takes place at the atomic level. So here you find atoms being located at the specific lattice positions of the crystal structure of the material. Now, when this is cooled to below MF, so there are four different figures, A, B, C, and D. A corresponds to a situation when the material is heated to above its AF temperature. So that means it is completely austenitic. It's completely austenitic. And now, when it's cooled to below MF, it tends to form what is known as twinned martensite or self-accommodating martensite or thermoelastic martensite. So what you see here is nothing but the twinned martensite. The martensite is formed in such a way that it shows twins. So here is, a twin boundary. So, and this phase is a mirror reflection of this phase. That's why the name twins. So twin boundary on either side of the twin boundary, things are identical. So this is a mirror reflection of this one. Similarly, this is a mirror reflection of this one. And this again is a twin boundary. So as you continue to deform, the twins travel, twin boundaries travel, and at one stage, it will become detwinned. It will become, so maybe you can think of a figure E, okay, you can imagine. So that will be representative of detwinned martensite, detwinned martensite, and the detwinned martensite upon heating will give rise to the shape change. To throw a little more light on shape memory effect. So in one of the earlier figures, I showed you a presence of four different or existence of four different variants, namely A, B, C, and D. So in fact, generally, you can think of 24 different variants. Okay. So in one particular domain, you can think of four variants. As you go from one to the other, you can think of again, four different variants. So in fact, 6 different domains amounting to 24 variants in all, in total, can be identified when it comes to shape memory effect. Now, for the sake of understanding, we imagine that there are only 2 different variants. There are only 2 different variants. So this is martensite. The martensite has 2 variants, namely 1 and 2. 1, 2, 1, 2, and 1, okay, and so on. Now, it is subjected to 3 different kinds of force. 1, tension, and 2, compression, and 3, bending. So you have a monatostatic structure consisting of 2 different variants, 1 and 2. Now, so in the absence of stress, there are only 2 different variants, 1 and 2. So no stress being applied. Now, when a tensile stress is applied, when the stress applied is tensile in nature, of the 2 variants, one grows at the expense of the other. For example, one grows at the expense of 2. One grows at the expense of 2. That means one expands, whereas 2 shrinks. This is as far as the application of tensile force is concerned. Moving over to this figure, in which you make use of, or rather you apply a compressive force. The opposite here happens. So instead of variant 1 growing, variant 2 grows here. Variant 2 grows here. Okay. Now, this is another situation. Now, go to the 4th one. So here, the material is subjected to a bending load. Bending load. And what happens? The variants grow according to whether the crystals are locally under tension or compression. As you can see here, at the bottom, so the crystals are subjected to compression. So these are the symbols that you make use of to represent compression. Whereas on the surface, the crystals are subjected to tension. So accordingly, the variants grow. So in one case, in the first case, no stress. In the second case, tensile. The third case, compression. In the fourth case, bending. Okay. So I have already discussed shape memory, two-way shape memory effect and one-way shape memory effect. Now we move on to discussing certain other things pertaining to shape memory alloys. Shape memory alloys exhibit shape memory effect. Shape memory alloys exhibit superelastic effect, and shape memory alloys can exhibit conventional behavior. I want to emphasize the fact that the same alloy, the same shape memory alloy can exhibit 3 different types of behavior depending upon the stress and depending upon temperature. So when the temperature is low, it can exhibit what is known as shape memory effect. When the temperature is higher, it can exhibit what is known as superelastic effect. And when the temperature is much, much higher, so here the temperature is in excess of MD. So I have already defined the 4 different temperatures, namely AS, AF, MS, and MF. And now I would like to define one more temperature, and that is MD. What is this D? What does this stand for? It stands for deformation. In other words, what is the meaning of MD? So MD is a temperature above which stress-induced martensite cannot be formed in the shape memory alloy. Please note that as far as the superelastic effect is concerned, this effect is given rise to because of the formation of what is known as stress-induced martensite. And the stress-induced martensite is generally formed about or around the AF temperature. So when it comes to the MD temperature, it is the maximum temperature up to which stress-induced martensite can be formed in the alloy, above which it will not be formed and the material will exhibit the conventional behavior. So this is again shown in the form of a three-dimensional diagram. So you find a stress on the x-axis, strain on the x-axis, stress on the y-axis, and then temperature on the z-axis. So three different phenomena are being represented. So let us take this particular one. So here the temperature is below MF. That means the alloy will exhibit martensite. The alloy will have martensite in its composition, in its microstructure. Now, this particular alloy is loaded. Okay, is loaded and then unloaded. So upon unloading, you find that so much of strain is left behind. So much of strain is left behind. And is it possible to get back the strain that's been imported? Yes. And that can be done by heating. So as you start heating, so as I travel along the temperature axis, I start heating the alloy. So as I reach this particular temperature, AS, it tends to form austenite. Martensite gets converted to austenite, and upon further heating, and when I reach AF temperature, it gets completely transformed to austenite. And this is what is known as shape memory effect. Now, look at this second one. So this is representative of the superelastic behavior. The first one, shape memory effect. The second one, superelastic effect. Now, I have reached the AF temperature. Now, I am at the AF temperature. Now, in the austenitic condition, I load the sample. I load the material, the shape memory alloy, and it shows this kind of a stress strain curve. That is, during loading, it forms stress-induced martensite, and upon unloading, it reverts to its initial shape. So the second phenomenon. Now, beyond AF, as I start heating, especially to above AF temperature, the material shows neither shape memory effect nor superelastic effect, and so it exhibits conventional behavior. To sum up, I can say that a shape memory alloy will exhibit shape memory effect only in a specific range of temperatures, only in a specific range of magnitudes of stress. So this actually has been already discussed, so I'll skip this. Now coming to the applications of shape memory alloys, there are many devices that are made using shape memory alloys, and these devices are dependent on these principles. There are 6 different principles that we are going to discuss now. First one, free recovery. Second one, constrained recovery. Third one, force actuation. Fourth one, proportional control. Fifth one, superelasticity. And sixth one, damping. So there are many devices based on these principles. For example, the blood clot filters are based on the principle of free recovery, and the hydraulic couplings that are used in fighter aircraft are based on the principle of constrained recovery, and the actuators that are used in the fire safety valves are based on the principle of force actuation, and fluid flow control valves make use of the proportional control. And similarly, for example, the catheters, guide wires for steering catheters into blood vessels are based on superelastic applications. And earthquake resistant structures make use of the principle of damping. So shape alloys can be used for a variety of applications. So we are going to look into the principles, the different principles. First, the free recovery. So what is the meaning of free recovery? It actually refers to the material's ability to freely recover its earlier shape, freely recover. So there is no constraint whatsoever. There is no constraint whatsoever. So I take a spring that's made of a shape alloy, and it is below its MF temperature. That is, it is completely martensitic. So please note that in the case of shape alloys, you have two different phases, and these phases have different nature. For example, austenite is strong and tough, whereas martensite is weak and ductile. So in contrast to the austenite and martensite that you come across in iron-based alloys. So here, below MF, you have martensite, and this martensite is, strained, deformed. Okay, so it undergoes a little bit of straining, and so there's a change in length. Now, what do? I release the load. What happens? The spring regains its, tries to regain its earlier shape, but not completely. So, in fact, you can neglect this small change that has come about. Now, all this happens below the MF temperature when the material is in its martensitic condition. Now, I heat the alloy or the spring to above its AF temperature. So you find that it has reverted to its earlier length. It has reverted to its earlier shape. And this is what is known as shape memory effect. And please note that shape memory alloys can show a strain recovery of up to 8%. And coming to, this is known as one-way shape memory effect. In the case of one-way shape memory effect, the material remembers only its high temperature shape, that is shape in austenite. And coming to the two-way shape memory effect, in the case of two-way shape memory effect, no load is applied, no stress is applied, and the material regains its shape just by heating and cooling. So look at this spring. So it is heated to above its AF temperature. So in this state, it shows a specific length. Now I cool it to below its MF temperature. So please note the change in length. So, and again, I heat it to above its AF temperature. You find that it has regained its earlier shape, earlier length, and that is known as two-way shape memory effect. So when it comes to applications, there are some applications for which you need alloys exhibiting only one-way shape memory effect, and there are certain other applications when you need alloys exhibiting two-way shape memory effect. So here is an example of shape memory alloys being used in medical applications. So it's basically a blood clot filter. Now coming to the composition, the alloy that is to be used should have biocompatibility. It should have corrosion resistance because it will be used inside the body. It's a blood clot filter. The main purpose of the blood clot filter is to get rid of arrest the clots from reaching the heart. Okay? So this might happen in the case of people with high cholesterol. Okay, so high cholesterol means more blood clots. So the blood clots should not reach the heart. It might be fatal. So to prevent that from occurring, so we make use of the SMA blood clot filter. This is also known as Simon Vena Cava filter, and it is made of nickel titanium. Nickel titanium shows not only shape memory effect and superelastic effect, but also shows corrosion resistance. It's also biocompatible. So as you can see here, so this is the size of the Simon-Werner-Ceva filter. So this is actually chilled and inserted into the appropriate location of the artery. So when it is inserted into the appropriate location of the artery, it picks up the heat from the bloodstream. It picks up the heat from the bloodstream, and it expands. It expands, and this is the final shape. So the exploded view is shown here. So it has an umbrella-like appearance. And so this portion can get rid of the blood clots. So this portion can be used to stop the blood clots from reaching the heart. Okay, so the figure here shows the photograph of the Simon-Werner-Ceva filter being located inside the artery. Okay, so please note that we cannot make use of other shaping alloys like copper-based alloys or iron-based alloys because they are not corrosion resistant, they are not biocompatible. The ideal material is, of course, nickel titanium shape memory alloys. So that's why nickel titanium shape memory alloys are used extensively in biomedical applications. Now, moving over to the constrained recovery applications. So what is the meaning of constrained recovery? Unlike in the earlier case, where we talked of free recovery, so here there is a constraint to the free recovery of the spring of the material. So let us again take the example of a shape memory alloy spring. So the temperature is MF, that is, it is in a morticity condition. It is now loaded. So it undergoes a change in length. It undergoes a change in shape. Now I release the load. Okay, it tries to regain the length a little bit, but it's only negligible. And all this happens in the morticity condition, A to B to C. All this happens in the morticity condition when the material is in the morticity condition. Now, going over from C to D, okay, after the release of the load, removal of the load, I put a constraint. And going from D to E, I heat the material. Please note this T above AF. Actually, in the absence of any load, in the absence of any constraint, it should freely recover its alloyed shape, but there's a constraint. So this will lead to the generation of stresses at both the ends. And so this is known as constrained recovery. And this principle is also used in certain applications. When you prevent the SM element from recovering, stresses up to 800 MPa can be generated. So such is the level of stress that can be generated by preventing an SMA spring from freely recovering. And this principle is used in pipe couplings in aircraft. In aircraft, especially the fighter aircraft, there are different pipes or different pipelines. Okay, some carry water, and these are known as water lines. Some carry fuel, and these are known as fuel lines. Some carry food, these are known as food lines, and some carry air, these are known as air lines, and so on. And they run from the front to the back of the aircraft. Okay. The length may run to many, many kilometers. But now, generally, now we have limitations when it comes to the dimensions of the pipe. Because when it comes to the length of the pipe, you have some constraints. That means you cannot produce a pipe which is infinite in length. So in order to overcome this, you go in for joining, you go in for welding. But it so happens that at the welded joints, the weldments tend to be defective. When the weldments or welded joints are defective, they may lead to leakage of, for example, the fuel, or a leakage of air, and so on. And this is not desirable. So in order to overcome this, we make use of what are known as sleeves, SMA sleeves. So and here the principle of constraint recovery is made use of. So I'm going to explain this to you. So here are the pipes to be joined. One pipe, another pipe. These are the pipes to be joined, and these are joined using an SMA sleeve or an SMA coupling. So there are different stages in doing this. So initially, the SMA coupling, so it has got the internal, I would like to mention two things here. That is the diameter of the pipe and the inside diameter of the coupling. Initially, the inside diameter of the coupling is made slightly smaller than the outside diameter of the pipes to be joined. Once again, the dimensions. The outside diameter of the pipes to be joined and the inside diameter of the sleeve. So initially, the inside diameter of the sleeve, which is made of a shapeable alloy, is made slightly smaller. Okay. Now, what do you do? Because the sleeve has to be slid over the pipes, okay, at this portion. So how do you achieve this? So it is actually, now the sleeve is immersed in a bath of liquid nitrogen. A bath of liquid nitrogen. So what does it do? When you immerse it in a bath of liquid nitrogen, in effect, you are cooling the material. You cool it to below its MF temperature. Shape memory alloys are softer in the monazite condition and harder in the austenitic condition. So in this, okay, now what do? You work on the inside surface. Okay, you work on the inside surface of the sleeve. Sorry, I do not have those figures here, and that's why I'm giving a lot more explanations. And so it is made slightly bigger. Okay, it's before it is slid over these two pipes, and so you remove the pipe. I'm sorry, the sleeve, which is made of a shape memory alloy, and it can be slid over the two pipes. Now the material has been removed from the liquid nitrogen bath, and so it will reach room temperature. It will attain room temperature. When it attains room temperature, what will happen? The reverse transformation will take place. That is from martensite to austenite. But please note that when it tries to return to the earlier shape, it can't happen because the pipes will prevent such a thing from happening. And so this will make the pipe much, in fact, in many cases, it do not require heating. It can take place even at room temperature. So you find that the pipe has been joined very securely, and it is very, very tight. It is leak proof. So this is one of the important applications of SMA couplings. And the alloy that is used is basically a cryogenic alloy whose transfer temperatures are much, much lower. I think even HAL Bangalore is making these couplings. And the composition of the alloy is NiTiFe. So when you use iron as one of the elements, one of the additions, the temperature comes down. Okay, so this is one of the applications. Next, actuator or work production applications. So here, the main purpose of the SMA is to do work, produce work. And to illustrate this, once again, a similar figure I like to make use of. So here is a spring. The temperature is below MF, that is austenitic. So in the austenitic condition, you load it and then you unload it. So from A to B to C, everything is in the austenitic condition. Now, after the load has been removed, after the force has been removed, you apply a load. You apply a load on the spring. So what happens? The material, okay, the material, oh, I'm sorry. So at D, you apply a load. You apply a load. What happens? And when you heat the material to above AF, it will expand. It will try to regain its earlier shape. And in the process, it does some work. And this is known as the actuator application of shape memory alloys. The SMAs are highly suitable for actuators and sensors. They make use of one or two-way shape memory effect. In particular, SMAs are made use of. Among SMAs, the NiTA alloys are much more popular because of three important properties. One, higher resistivity, higher stresses, and higher strains. And they're used in on-off applications. And they're also used in commercial on-off actuators, which are small in size. And the actuation is done using electricity. So what I want to drive home is that shape memory alloys are used both as sensors and as actuators. And the actuation can be done using electricity. There are certain actuators which are known as thermal actuators, and there are certain actuators which are known as electrical actuators. Electrical actuators are those ones, which are energized by passing an electric current, whereas the thermal actuators can respond to natural conditions. That means ambient heat. What are the advantages of using SMAs in actuating mechanisms? There are many points, but what I want to impress upon you is that unlike the conventional actuators, the SMA actuators are simple in terms of principle, simple in terms of construction, and simple in terms of operation. And most importantly, the stroke and force can be easily modified by using the right SMAs. For example, the actuator can be as small as a wire, an SMA wire, which can be actuated by using an electric current. The second important advantage is their cleaner to operate. They're silent to operate. They do not produce any sparks, and they can work under zero gravity working conditions. Please note that there are many actuators which are bigger in size. Not only are they bigger, but they can also produce dust. And they produce noise. Whereas in the case of shaper metal alloys, you find that there is no dust, there is no noise, okay, and no spark generation. In certain applications, you need to be very, very careful. For example, shaper metals are also used in the petroleum industry. Okay, in such situation, during operation, no spark should be generated. Otherwise, it will prove to be very dangerous. So they can work completely spark-free, and they can work in zero gravity working conditions. So that is why, the so-called Mars Pathfinder, and such devices can be used. They can be used in zero gravity working conditions. Then other advantage is high power to weight ratio. High power to weight ratio. The actuators are very small in size, but then the power that they produce can be much, much larger. So please look at this particular graph. So it compares the power to weight ratio of the conventional actuators with that of the SMA. So SMA produce a high power, but the weight is much, much smaller. Much, much smaller. So to summarize the important advantages of using SMAs in actuators: simplicity, compactness, and safety. Second one, clean, silent, spark-free, and zero gravity working conditions. Third one, high power to weight ratio. The fourth one, excellent corrosion resistance, especially the actuators that are based on nickel titanium are highly corrosion resistant. Moreover, they're also highly biocompatible. Please note that both sensors and actuators can be used within the body and outside of the body, especially when the actuator is to be used within the body in the form of a medical device. Then it's all the more important that the actuator is biocompatible. And in the case of nickel titanium, you find that they're highly biocompatible. So just to give you an idea of the size and shape of the actuators, so please look at the size of the actuators. NATI-CU cantilever actuators used in anti-scald safety valves. And this one, memory shaped anti-scald shower valve. What is the purpose of this shower valve? So the shower valve's main purpose is to, control the temperature of water, which is used for bathing. So at the faucet, shower faucet, water should be delivered at a particular temperature. The temperature should be neither high nor low. And that purpose is achieved by such a small part as this. So the actuator makes use of, a small plate-like thing, a small strip made of NATI-CU. So look at, this is this is an American coin, and this is the strip that is used within. Example for actuators. Again, in in industrial safety applications, okay, you can make use of shape memory alloys. The main purpose of this is to sense, the temperature of the room. So in the case of any smoke, okay, so the temperature of the room may shoot up. So in such situation, so you have to take the appropriate safety measure. So what do you do? So once it senses that the temperature of the room has shot up, let's say 60 degrees centigrade or 70 degrees centigrade, it will open the sprinklers and the fire will be doused. So that's the main purpose of the fire check industrial safety valves. And smart composites. So your FDP also has to do with composites, and shape memory alloys are made use of in smart composites. So in the case of the conventional composites, you make use of reinforcement. Okay, and in the case of smart composites, again, you make use of reinforcements, but the reinforcements are made of memory elements, shape memory alloys, maybe in the form of wires, or maybe in the form of particles, or maybe in the form of thin films, and so on. So, and smart composites are really advantageous. So there are many advantages that can accrue as a result of using shape memory elements in a matrix. The matrix could be a polymer, or could be a ceramic, or could be a metal. So these are some of the advantages that we can derive. One, larger reversible strengths, generation of high stresses, large reversible changes of mechanical and physical characteristics, ability to generate gradually stresses and strains, and structural integrity. So these are the advantages that we can gain by using smart composites. And in addition, you can also generate some novel characteristics. What are these novel characteristics? First, upgraded shape memory characteristics. That means the amount of strain recovery can be made higher. The shape recovery can be larger, and we can make it less sensitive to degradation. Second one, upgraded structural characteristics. This is a very, very important one. Self-repairing characteristics resulting in an increased resistance to fatigue and buckling of polymer matrix composites. Self-repairing characteristics. So in the case of any cracks developing in, let us say, a dam or in a bridge, these shape memory alloys have the self-repairing capabilities. And the other important property is ability to adjust shape, combination characteristics. Example, structural polymer matrix composites with adjustable shape. And the fourth one, completely new product characteristics. For example, you can change the stiffness. Polymetric composites with adaptive stiffness and frequency modes. And design of smart composites. So we need to have the appropriate knowledge and predictive capabilities. So that's the first prerequisite. And the second prerequisite for the design of smart composites is a knowledge of SMA matrix interface and stability of cyclic applications. And apart from this, the thermomechanical behavior of SMA is nonlinear with hysteresis. This is to be borne in mind because SMAs do not exhibit a linear behavior. So whenever you design a device or whenever you design a smart composite, you need to take into account all these factors. Thermal SMA actuators in automobiles. As I said earlier, actuators could be of different types. The thermal actuators can respond to the ambient conditions. They can work at room temperature. Okay, so there are many parts in an automobile that are made of SMAs. So as you can see here, radiation shutter, climate control, suspension adjustment, 6 brake ventilation. So there are many parts, okay, whose functions are controlled by the use of SMA actuators. So here are some typical SMAs used in the automobiles. So different alloys exhibit different characteristic transformation temperatures. They have different ranges of temperature. So here is an alloy whose hysteresis width is much lower. It's only about 15 degrees, this one. And the standard NATA can show a hysteresis ranging from 30 to 50 degrees centigrade. And electrical SMA actuators in automobiles. So here, the actuation is done by using by passing an electric current. So as in the earlier case, so here also there are many parts that make use of SMA actuators. The fog lamp louver, this one. Then the engine hood lock. Third one, retractable headlight, and so on. And shape metals are especially used in stealth aircraft. You know the meaning of stealth, okay? I mean, secret, okay? So, for example, the tailless military aircraft using smart materials in checkerboard area, then twisting wing, expandable fuel cell, and compliant trailing edge. So the main purpose of using shape memory alloys in stealth aircraft is that the aircraft should be in a position to enter into the enemy territory without being detected. Okay, so they have an appropriate shape. Okay, they have an appropriate shape. So the main thing about detection using radar is that electromagnetic waves are being sent forth, and when they hit upon the aircraft, I mean, the electromagnetic waves are reflected back, and the reflected waves are captured and analyzed. And so this may reveal the location of the aircraft, and that may not be a good sign. So in order to overcome that, we make use of shape memory alloys in what are known as smart aircraft. This is known as stealth aircraft. Stealth aircraft can fly in the skies without being detected. So second one, flappable stealth aircraft. So when it comes to the conventional aircraft, you have a couple of wings, and these are stationary wings, and these can't be moved about. But in the case of the flappable stealth aircraft, the wings have the ability to be flapped about. There are some advantages that can result when you make use of the flappable stealth, flappable wings. Just like a bird, the wings can be flapped about. I have learned that by flapping about the wings, you can generate more momentum. And this one thing. And secondly, perhaps the aircraft can escape detection by the enemy radar. And other one, SMEs are also used in stealth submarine. So the main thing about the submarines is that they should travel underneath the sea without making much of a noise, rather without making much of turbulence. So you should, the submarine should travel underneath the sea just like a fish, okay? Just like a fish. So look at this one, okay? So it has many segments. It has many segments, and so these submarines make use of shape memory alloys. They travel, they move about the sea, underneath the sea, without making much of turbulence. If turbulence is created, it will leave behind a signal, and the signal can be detected by the enemy radar. And so that should not be encouraged. And that is why in the stealth submarines, the shape memory alloys are made use of. This is also a similar stealth aircraft and stealth submarines. So because of shape memory effect, the tail can swish about from one side to another. And as in the case of, see here, just like the body of a fish, okay? So by, passing current, an electric current, the shape can be changed. And so it can move underneath the sea without making much of a noise. And Mars Pathfinder. So from the Earth, now you can control the movement of the Mars Pathfinder. And in the Mars Pathfinders, SMA waves are used to control the movement. So Dr. Raju, I'd like to know as to how much time I'm left behind. Dr. Raju, can you hear me?
Yeah. Yes, sir. Yes, sir.
What is the time left?
It's actually 1 minute to end, sir.
1 minute. 1 minute.
Yes, sir. It's 10:59. 11 o'clock is the time, sir, to stop.
Okay. So in that case, I'll have to skip some slides.
Okay. Yeah. Some people have few queries. Somebody has raised the hand during the talk. Okay. Shall we leave for a question and answer session now, sir?
I will cover a few more and then we can go in.
Okay, sir.
I'll skip some slides also.
Okay, sir.
Okay. So, second one, superelastic application. So here, as we have already seen, the material, shows this behavior in the austenitic condition. It shows this behavior in the austenitic condition. So some example, for example, there's so-called eyeglass frames. So look at this. Look at this. So this is a hinge, and this hinge can be wound around your finger, and you can put it in your pocket, or you can fold this thing and put into your pocket. Okay, but when you take it out and put in warm water, it will regain its original shape. So no damage whatsoever. And so maybe the damping is one of the important applications for shape memory alloys. So this property is being made use of in some structures, especially to restore the functions of some old buildings. Here, I compare the force versus time for two different materials. One, a conventional material, namely an aluminum bar, dotted lines, and two, solid NATI bar. So as you can see here, the NATI bar pulses the vibrations. It suppresses vibration to a greater extent. So as you can see here, the shape memory alloy device made of nitinol wires are being made use of to protect a church. It is known as the Basilica San Francisco in Assisi, Italy. It was actually damaged by an earthquake. So in order to restore the structure, the structures were reinforced with some shape memory elements. So this again the bell tower of this Church of San Giorgio, Italy. Okay, so I'll stop with that. Maybe I have a couple of videos to show. Shall I go ahead with that, or I'll answer and then go ahead with the videos? Please let me know.
We will take question and answer, sir. Then we will see at the last, sir.
Yes. Okay, fine. Yeah.
Yeah, dear participants, if you have raised your hands during the session, if you have any specific queries, you can just clarify with the professor. He will clarify your doubts. Sir, Amar Mahoto has asked a question. What weight percentage of copper, titanium, nickel should?
The question is the composition of nickel, titanium, copper.
Yes, sir.
Right? Okay. So the amount of copper can vary from 5 to 15 weight percent. The amount of copper can vary from 5 to 15 weight percent. And if you add, let's say, only 5-8% of copper, it does not bring about much of a change in terms of transformation temperatures. Please note that in the case of shape memory alloys, the transformation temperatures are very, very important. And you choose the alloys based on the transformation temperatures. For example, in the case of equiatomic nitinol, that is, it has got 50 atomic percent of nickel and 50 atomic percent of titanium. The AF temperature is 37 degrees centigrade, okay, which is closer, or which is nothing but the body temperature. And no wonder this alloy, the binary or the equiatomic nickel titanium alloy, can be used inside the body. That is in vivo applications. There are two different types of application: in vivo and in vitro. In vivo means inside the body. In vitro means outside the body. For example, in the case of the cardiovascular stents, the stents are to operate at a temperature of 37 degrees centigrade. And so the nickel titanium alloys with 50 atomic percent of titanium and 50 atomic percent of copper fulfill this requirement. And when you bring in an element like copper, the transformation temperatures are affected. But then up to, let's say, 5-8% of copper, up to 5-8% of copper, there's not much of a change in the transformation temperature. But then there could still be a slight change in the transformation temperature. So this is about the nickel, titanium, copper alloys. And also, there is a phase, there's a new phase could also be formed with the introduction of copper-based alloys. Sorry, with the addition of copper as an alloying element. So you should be very careful about the phase transformations that may be brought about by the addition of a third element. Have I answered your question? I hope I have answered your question. If you have, if you still have any doubt, you can please ask me. Okay. What is this?
Second, sir. One second.
Yeah.
One
What is it? Oh,
Sir, am I audible?
yeah, please.
Yeah. Is there any lifetime for SMA?
Of course. Of course. See, actually, shape minerals undergo what is known as degradation. What do you mean by degradation? There are two properties which are important when it comes to shape minerals. One is shape recovery strain. Another one is shape recovery stress. Okay, with the continued usage of time, you find that the recovery strain comes down, and so is the case with recovery stress. And so this is called degradation in shape memory effect, or this is also called functional fatigue. So you know what is meant by fatigue. Okay, so in the case of conventional materials, now we say that on continued application of load, the load-bearing ability of the metal comes down. Similarly, in the case of shape memory alloys, especially in the case of nickel titanium shape memory alloys, with continued use of the alloy, the amount of strain that it can undergo and the amount of stress that it can generate decrease. And this is known as functional fatigue. This is a problem with respect to shape memory alloys. And so there are some heat treatments that are being used so as to overcome the degradation that occurs, the functional fatigue that occurs. In fact, it's a very big topic when it comes to shape memory alloys. And one of my research scholars, PhD scholar, is working on the functional fatigue behavior of shape memory alloy or shape memory alloys. So very nice topic, very, very interesting topic, because shape metals are used extensively for many, many applications. And it's all the more important for us that we overcome the problem of degradation or functional fatigue.
Sir, one more, same Amar Mahato has asked, also explain IACS percentage of that composition.
Which composition?
Please explain electrical conductivity in IACS percentage. Mahato, can you tell me what is this IACS percentage, what you're asking about? Can you please type? Mahato? Or you can unmute yourself and ask the question.
Yeah, you can pose the question straightforward. You can ask.
Amar Mahato, are you online?
Use your microphone. You can be more,
he is telling explain electrical conductivity in IACS percentage.
What is it to explain electrical
What he means by IACS?
No, I don't think this question is very much relevant. I don't know. Maybe he doesn't understand what he wants to know. I mean, it's not clear.
Yeah. Any queries? Any further queries?
See, one thing, so when it comes to shape memory alloys, so you need to heat the alloy. Why do you heat? Why do you heat the alloy? Because when you heat the alloy, okay, it can undergo phase transformation. Please note that shape alloys are based on the principles of phase transformation occurring. No? That is austenite to martensite and martensite to austenite. Okay, and for the phase transformations to take place, you need to heat the alloy to the austenitic temperature. And how do you heat? It is by supplying an electric current. And so the electrical resistivity is an important property, not electrical conductivity. Okay, so electrical resistivity is very, very important. And if it is conducting, it will only be helpful in conducting, but it will not help the material to get heated up. Why do you want to pass electric current? You want to pass electric current so that the material can get heated up, so that it undergo phase transformation, so that the phase, the shape changes can take place. I think this is more relevant than what you are asking. Yeah.
Sir, can you hear me?
Yeah. 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 Who is this, please? Yeah. Please, you can put your question straight away. Other questions, please feel free to ask me. I'll be happy to answer your questions. Now, if you have not understood any particular slide, any particular part of the presentation, feel free, because time has been my.
Amar Mahato, you are online. You can ask you what is your actual question.
Yeah.
You are told, okay, sir.
Yeah. What is
What do you mean
your
by
question,
IAS
please?
percentage? Okay.
Yeah.
If you
Feel
if
free.
it is okay for
because
you,
the subject may be new to you.
sir, shall we stop here, sir?
But I appreciate questions.
Hello.
Okay. So if there are no questions, I would like to move over to the videos.
ಹೋಯ್ತಾ ಇಲ್ಲೂ ನಿಮ್ಮ ಮೊಬೈಲಲ್ಲಿ ಹೇಳಿ.
Hello.
Yeah, please. Yes. Yeah. Please introduce yourself and no, post the question.
Sir, am I
Am
audible?
I audible, sir?
Yes, you are audible.
Yeah.
Post your question.
I think if no questions are there, shall we wind up, sir? With your kind permission.
Don't hesitate to ask questions. Yeah? The subject may be new to you. Documents may be new to you. The principles may be new to you. But never mind. Ask questions. However simple they are, I'll be happy to answer. It appears there are no further questions. Yeah, so that's the case. We'll move on to the videos. So there are 3 videos I have. I'll present them to you.
Okay.
So video ಹಾಕಿದ್ದಾರೆ ಸರ್.
Is this? Yes? I'm calling up 2 hours. I'm busy. So one more video. So that brings us to the end of the video presentations. In case you have any other queries, feel free to ask me now before we conclude.
I think no queries, sir. You have
Okay.
explained very well. Thank you very much, sir, for giving such a wonderful talk on shape memory alloys. Look forward for you to give some more talks in near future in the coming FDP, sir. Thank you very much, sir.
Thank you. Thank you.
Participants, the link for attendance is shared. Please fill it and send it, sir.
So this will be uploaded into the ATAL website, is it?
Yes, sir. Yes, sir.
Is it possible to edit? I'm
Okay.
just wondering, maybe.
Okay. Before uploading, I will just contact you and try to do whatever necessary things is required.
Yeah, because I want to have the maximum clarity.
Okay,
and
sir.
when I deliver a talk, it's altogether a different ball game. But
Okay.
when I deliver a talk online, it's slightly different.
Okay, sir.
And so let me see how best it has come out. And so
Okay.
depending upon the need, we might as well edit
Okay,
here
sir.
and there and then upload. I think that may be
Okay,
the
sir.
best part.
Okay, sir. Okay, sir.
Thank you so much. So all
Okay.
the best
If possible, you
for
can share the this one PPT also, sir. Some participants are asking for PPT.
okay.
If you want, you can please share so that I can share with the participants, sir.
Okay. Okay. After the talk, maybe I'll see what to share and what not to share, and then
Okay, sir. Okay, sir.
I'll let you know. All right.
Okay, sir. Thank you, sir.
Thank you so much for the wonderful opportunity, and wish you all the very best with the FDP and with the other sessions.
Okay, sir. Thank you. Thank you, sir. Thank you very much, sir.
Welcome. Bye bye. I sign off.
Bye.
Yeah.
Okay, sir. Thank you, sir.
ಹೇಳು ಸರ್ ಅವೇರೆ ಕೂರು ಕೂರು ಸರ್ ಹೇಳ್ಬೇಕು
Hello, good morning, everyone. Devendra sir, are you there? Hello.
Yeah, hi. Yeah, I'm there. Yeah, I'm here.
Yes, sir. Thank you. Sorry. Uh, Good morning, everyone. The second session will be starting at 11:30, and the speaker is Dr. Devender Yadav, and his research areas are flash sintering of ceramics, thermomechanical processing, electron microscopy, EBST and texture, friction stir processing, structure properly correlation, and is having awards and honors of All India Gate rank 34th in Engineering Sciences paper in 2007, Best Paper Award in International Symposium for Research Scholars ISRS 2012, Best Paper Award in International Symposium for Research Scholars ISRS 2014, IIT Madras Research Award in recognition of quality and quantity of research work carried out during PhD April 2015, and also is a member of professional bodies Indian Institute of Metals, Electron Microscopy Society of India, and also he has written books on metal matrix composites by friction stir processing, Butterworth Enerman elsewhere, PP 138 2017, and also he has done so many publications. Sir Devender sir, I welcome you, sir, and you can take over to the presentation, sir.
Okay.
Yeah.
Well, thank you so much for the invitation, and thank you for organizing this FDP. When my friend Dr. Raju invited me, I could not say no to him.
Yeah.
The thing is, like, I'm not really feeling fully well today. I'm slightly down with cold, but let's see how the session goes. So I'm going to share my screen, and so I've got a system with multiple monitors. So I'm going to lift this side. Okay. Okay. So if you all can hear me and if you can see the slide, please let me know. Dr. Raju.
Yes, sir.
Is it visible, sir?
Yeah,
Okay.
it is visible, sir.
Right. Okay, so good morning, everyone. I'm Dr. Devender Yadav from Department of Metallurgical and Materials Engineering at IIT Patna. Now, the title of this talk is Non-Equilibrium Composites by Friction Stir Processing. Now, I must tell you here that this is something, it's not a new work. This is something which I did during my PhD. So it's, I would say, something like a long time back. Currently, I have shifted to ceramics. So nowadays, I don't work on FSP anymore. I mostly work on ceramics. So what I'm going to share with you today is something which is not really new. Okay. Right. So this is the outline of the talk today. We'll start with the background of the study, followed by introduction and experimental details. I'll then share with you some of the results on microstructure development of the non-equilibrium composites and what is the mechanism of grain refinement. We'll also look at the mechanical properties, and at the end, we'll look at the thermal stability of microstructure and of the reinforcement particles in this non-equilibrium composites. All right, now when it comes to aluminum and its alloys, the single most important property which makes them very attractive is their high specific strength. That is, they have got a very high strength to weight ratio. Now, aluminum and its alloys are widely used in aerospace, automotive, and several applications. Now, several methods have been developed to improve the mechanical properties of aluminum and its alloys. Now, these includes like grain refinement, strain hardening, precipitation hardening, solid solution strengthening, thermomechanical treatments, and metal matrix composite technology. Now, the first five methods, there is a limit up to which you can improve the strength of aluminum alloys. Now, with the sixth method, that is the metal matrix composite technology, you can further improve the mechanical properties of aluminum alloys beyond what the first five methods can give you. So in metal matrix composite technology, what we usually do is we incorporate high strength and high modulus ceramic particles such as silicon carbide, alumina, boron carbide, aluminum nitride, and things like that to aluminum and its alloys. The aim is to get a good combination of strength and ductility. But the problem is now these ceramic particles, they are inherently brittle. That means they do not have good ductility. These particles also have a low coefficient of thermal expansion, which is significantly different from aluminum matrix. And they also have a different nature of bonding altogether. They have non-metallic covalent bonds, mostly like it is ionocovalent bonds. So what really happens is when you incorporate these high strength and high modulus ceramic particles into aluminum matrix, your strength increases. Okay. Now, this is always accompanied by a large drop in the ductility of the composite. So you get improved strength, but it comes at a cost of a significant reduction in the ductility of the composites. Now, the main reasons for the drop in ductility are are these like poor wettability of these ceramic particles. So these ceramic particles are not having very good bonding with the metallic aluminum matrix. Also, some of few times what really happens is these ceramic particles they are not uniformly distributed in your aluminum matrix. They are like present in small clusters. Next thing is, since the interfacial bonding is sometimes weak, it leads to interfacial debonding. So if the interface is weak between the ceramic particle and the aluminum matrix, there is not a efficient load transfer. Okay, and because of these reasons, basically, the ductility of the composite is uh, dropped. Now, so we asked ourselves a question that can metallic particles be used as reinforcement in aluminum, in the place of ceramic particles to get a good combination of both strength and ductility? Because hard metallic particles are strong at the same time they're also ductile. They're not brittle like the ceramic particles. So when we asked ourselves this question and when we refer to the literature, we found that the answer to this question is actually no. Why? Because if you look at the phase diagram, then you can classify the metals in two categories: the metals which have high solid solubility in aluminium and the metals which have got low solid solubility in aluminium. Now, the metals which have high solid solubility in aluminium, they dissolve into aluminium, and what they do is when they dissolve into aluminium, they form solid solution. The metals which have low solid solubility in aluminium, they actually react with aluminium to form intermetallics. Now, these intermetallics are again brittle. They are just like ceramic particles, so we don't want them, right? Now, but somehow if you can prevent the reaction or the dissolution, then the answer to this question becomes yes, that metallic particle can be used as reinforcement in aluminium. What you need to do is you have to prevent the reaction or the dissolution of these metallic particles with aluminium. So whatever metals you're going to use as reinforcement in aluminum matrix, it should not react and it should not dissolve into aluminium. If these things happen, then you end up either with a solid solution or a intermetallic phase. You don't form a composite material. But it's not so simple. This is a big challenge. How do we really prevent the reaction or the dissolution? Now, if you look at conventional composite preparation routes, the two most widely used routes are powder metallurgy route and the casting route. So in powder metallurgical route, what we really do is we take powders of the metal, which is our matrix material, and we also take powders of the reinforcement. We mix them together and then we subject them to sintering at high temperatures to get a dense body. But then when you have to sinter this powder mixture of metal and another metal, let's say, then what's going to happen? These two metals are going to react because your sintering is actually a time consuming process. Sintering usually is done at high temperatures and it takes many hours. So at high temperature, again, these metallic particles can dissolve into aluminum or they can react with aluminum. The same problem comes in the casting route as well. So in the casting route, what we do is we melt the matrix material. In this case, it's aluminum, let's say, and then to the molten aluminum, we can add these hard metallic particles. But then the molten aluminum temperature is going to be higher than 660 degrees C because the melting point of aluminum is 660 degrees C. So in the liquid state, aluminum will be at a temperature of more than 660. At that temperature, when you add these metals, what's going to happen? Again, the metals which have high solid solubility in aluminum, they're going to dissolve into aluminum to form a solid solution, and the ones which have low solid solubility in aluminum, they will form intermetallic. Okay, so the conventional composite preparation routes, they are sort of ruled out. Of course, you can always try one thing. In the casting route, the moment you add these metallic particles, you can subject it for rapid cooling to prevent the reaction. So the moment you add the metallic particles, immediately go for casting and what is called as rapid cooling. You can check if the reaction is prevented at all. Now, when we looked at literature, we found that there are not too many routes by which you can incorporate metallic particles into aluminum matrix to form a composite. Professor Manoj Gupta, he's well known in the field of composite materials. Uh, he's at National University of Singapore. So he developed a method which is called as disintegration melt deposition. What it does is he spray atomizes this molten aluminum, and then when the spray is actually going to fall on a substrate, at that point through a another nozzle, he incorporate these metallic particles into the spray atomized aluminum. In that process, basically what you do is you are minimizing the time for reaction of these metallic particles with molten aluminum, and immediately everything falls on the substrate, which is actually at a significantly lower temperature, so you don't allow the metallic particles to react with the aluminum matrix. uh, I mean, in his work he first tried to incorporate titanium particles into aluminum matrix to process aluminum titanium composites. The main outcome of his work was that he could not prevent the reaction even by forming a oxide layer on the titanium particles. Okay, and the ductility was significantly reduced. So if you look at the strength of pure aluminum and then the strength he got after preparing a composite of aluminum 6% titanium, there was a good improvement in the strength, but there was a significant decrease in the ductility. The ductility of the composite dropped to something like 18% from 35, which is like something like 50% drop. Now, in his group, they again tried with two more metals. They have reported, even trying to incorporate nickel particles into aluminum matrix and also magnesium particles into aluminum matrix. So if you read their papers, the main conclusion is that it is impossible to prevent reaction. Okay, so the reaction is basically impossible to prevent. Okay, some reaction will always happen. So some amount of titanium will always react with aluminum to form intermetallics. Al3Ti. Same case will happen with nickel. It will form Al3Ni or AlNi type of intermetallics. Now what we did is we looked at this problem from a different perspective. We thought that we should not go to liquid state at all. So even if you want to incorporate these metallic particles into aluminum, the best would be to process this composite in solid state. Because if you go to solid state, then the diffusion rates are very slow in solid state and your temperatures will be far lower. So the technique which we use to incorporate the ceramic particles into aluminum matrix is called as friction stir processing. It's not a new technique. The process was invented in the year 1991 at the Welding Institute in UK. In the beginning, it was primarily used for frictions. It was developed actually as friction stir welding technique, where we wanted to join two plates in solid state. What we did is we carried out friction stir processing where we don't join two plates, rather we carry out the processing on one plate. Okay, so in this particular process, some of you may have maybe familiar with friction stir welding and processing. So let me tell you what really happens here. So in this process, what we do is we use a specially designed tool which has got a pin at its bottom. Okay, now the tool is made to rotate at high speed. Okay, the tool rotates at high speed, and then you apply a downward force on the tool. Okay, and then this pin goes into the base material. The pin is pushed into the material, and this part, this is called as the shoulder. The shoulder touches the surface, and then the tool is made to traverse by a particular feed rate. So what really happens is in this region there is a lot of material mixing. Okay, so this material get mixed uniformly or very nicely, and then the tool moves forward. Now this particular process has been widely used as a grain refinement technique. That is, you can achieve very fine grain size in the process region if you start with a very coarse grain size. So the process has been used for microstructure, even homogenization in the case of cast alloys. So if you want to remove the casting defects, then also you can carry out this process. Now FSP is actually a thermomechanical process. Okay, it is a solid state process. The material do not really melt. Okay, but it becomes plastic. So when you go to very high temperatures, the matrix material becomes soft and it becomes plastic, and that plasticized material it flows around the pin. Okay, and so that's what leads to the mixing of this plasticized material. The process is not really a room temperature process. There is a significant temperature rise. Okay, now the temperature rise depends on the ratio of your rotation speed to the traverse speed. So at what rate your tool is rotating, okay, and then at what rate the tool is moving forward. This ratio really governs the temperature. Now, what we always desire is we want fine grain size in the what is called as the stir zone. Okay, so this process region is called as the stir zone. We always need fine grain size. Now, why do we need fine grain size? Because the metallurgist people know that according to the Hall-Petch equation, if your grain size is finer or small, your properties would be better. Your strength and hardness they improve. So if you go for a higher ratio, what will happen? The temperature rise will be more, and if the temperature rise is more, it will lead to grain coarsening. What I mean by grain coarsening is that it will lead to grain growth. Now, if your grain size grows, then you're going to get less strengthening. So you can always do one thing. You can reduce this ratio so that your temperature rise is less. So if you go for lower ratio, you're going to get fine grains. But then you cannot keep decreasing this ratio thinking that, oh, if I decrease this ratio, then I would get even finer grains, or let's say nano grains. Because if you go for a ratio below a optimum limit or below a optimum ratio, it will also give you defects here. That means the material is not plasticized enough. It is not going to flow around the pin properly, and when that happens, you're going to end up defects. You're going to end up getting defects. So there is always a optimum ratio. Okay, and that optimum ratio will decide your what is the finest grain size you can achieve. Okay, now what we really did is we classified metals, some of the prominent metals, into two categories: the metals which have low solid solubility in aluminium and the ones which have high solid solubility in aluminium. So the metals which have low solid solubility in aluminium, that means they react with aluminium and they form intermetallics. Sorry. And the metals which have high solid solubility in aluminium, they actually dissolve into aluminium to form a solid solution, just like a liquid solution. Now here in the solid state, we form solid solution. What we did is we picked one metal from each case, each group. So we picked up titanium from this one and we choose copper from this one. The reason for choosing copper is copper has got higher melting point than aluminum. So during FSP process, we do not want the reinforcement phase to go close to its melting point. Okay, so copper has got a higher melting point, 1083 degrees C. Now the methodology what we use to process composite. Now, how did we incorporate these metallic particles into aluminum matrix? What we did is we made a groove on the aluminum plate. The width of the groove was 1 millimeter, the depth was 2 millimeters. And then we carried out FSP along the groove. Okay, now these are the two geometries. And after FSP, so we started with commercially pure aluminum plate. Pure aluminum is very weak and not very hard as well. We choose pure aluminum because if you pick alloys, there are other problems, whether it's a precipitate hardenable alloy or not. And this was sort of a first study of its kind, so we started with pure aluminum. That was another reason. So once we carried out FSP, this region actually formed a composite. And then the composite was characterized for its microstructure through XRD, SCM, EBSD, and TEM. And for the mechanical properties, we performed tensile test on the process composites. We also looked at thermal stability, like up to what temperature the microstructure is stable, and up to what temperature the metallic particles are stable in aluminum matrix. And the thermal stability was evaluated through microscopic examinations by SCM and EBSD. Now, we started with titanium powder in the first case. We procured the titanium powder from Alpha Acer, where the average particle size was 35 micrometer and the particle size ranged from 5 to 70 micrometer. So the size distribution was actually quite a lot. I mean, it was huge. So we carried out FSP at a tool rotation speed of 1000 RPM and the tool traverse rate was 30 millimeter per minute. So the first thing what we did is we looked at the XRD pattern of the composite, and there we got peaks corresponding to titanium and aluminum. We really did not observe a peak of intermetallic. So it means that titanium did not react with aluminum and titanium was retained in its elemental state. So if you prevent the reaction of titanium with aluminum, you're going to end up with a composite of aluminum and titanium. So we looked at the microstructure, both in the surface and in the cross section of the slit zone, and we got a uniform distribution of these titanium particles. Now, these are all the backscattered electron images taken from a SCM, where all these white particles, what you see, they are all titanium particles. They all appear bright because atomic number of titanium is much higher than that of aluminum. So this is the aluminum matrix, and the bright particles, what you see here, these are all titanium particles. The area percentage of the titanium particles was around 7%. We looked at the particle matrix interface at high magnification, and we found that the interface was actually very, very clean. So this is our aluminum region, and this is our titanium particle. And if you look at the interface, it's quite clean. I mean, there is no sign of any reaction happening between aluminum and titanium. Now, this again indicates that we can retain the titanium particles into aluminum matrix by FSP. Okay, so basically we have prevented the reaction of titanium and aluminum, and that is the reason why titanium is retained in its elemental state in aluminum. Now we call this composite as non-equilibrium, because if you look at the phase diagram, under equilibrium conditions, titanium would actually react with aluminum to form Al3Ti type of intermetallics, because the maximum solid solubility of titanium in aluminum is around 1 weight% only. Why did the reaction not happen is because FSP is a solid state process. None of the phases goes to solid state, and also it's a fast process, so the material experiences the peak temperature for a short time. In that short time, titanium cannot react with aluminum to form some stable, intermetallic compounds. So that's why we call these composites non-equilibrium. We performed the EDX analysis on these composites to see the distribution of titanium particles, and we found that there was a good distribution, or you can say uniform distribution of the titanium particles in the aluminum matrix. So here the aluminum matrix is represented by green color, and all these red color particles, what you see, they're all titanium particles. We looked at some individual particles at high magnifications, and here also we found that the interface was actually clean. You can see only red color up to this point, and beyond that it is green. We do not see a region where both the colors are present. So this also indicates that titanium did not react with aluminum, and titanium is retained in its elemental state. Of course, you can always argue that uh, there could be a very thin layer, let's say a few nanometer thin. But then our argument would be that even if a thin layer is present, thin layer of reaction product is present, that would actually improve the bonding between aluminum and titanium, if at all it is present. Okay. Uh, so we do not rule out the possibility of reaction. There could be some reaction because uh, we always have the limitation in the microscope. What is the smallest feature what you can see? So 1 to 2 nanometer thin layer may be present, but then again it's not harmful. It would only improve the properties because it will improve the bonding between aluminum and titanium. We looked at the microstructure of the composite in detail. So for example, if this was our stir zone, we looked at the microstructure on the advancing side, the retreating side, and in the cross section, and also in the center of the stir zone. So we looked at the microstructure on the surface and also in the cross section of the stir zone. So we performed EBST analysis, that is called as electron backscatter diffraction. It gives you this beautiful maps like this, colorful maps, where every color represents the orientation of the grain. So in these microstructures, if your grain appears, let's say, blue in color, it means that it has got 1-1-1 orientation. If the grain is in red color, it means it has 0-0-1 orientation. If it is green, it is 1-0-1 orientation. Okay, so what we can say is we see sort of uniform or homogeneous microstructure at all the locations in the stir zone. All these black particles, what you see, these are all titanium particles. EBST, the issue is when you prepare the sample by electropolishing, it will polish actually one of the phase. So in this case, aluminum phase was nicely polished, but titanium was not nicely polished. So that's why we did not get good pattern from the titanium particles, and that's the reason why all these titanium particles, they appear in black color. Now let's look at the microstructure in a little more detail. So this was the microstructure of the base aluminum, the starting aluminum, okay, where the average grain size was something like 90 micrometer, and the percentage of high angle grain boundaries was around 94. So this was actually a well annealed microstructure. Now, if you look at the microstructure of the composite, ALTA composite, this is a titanium particle. The average grain size of the aluminum matrix in this case, in the composite, was actually 6 micrometer. So FSP has done two things. The first is it not only incorporated the titanium particles into aluminum matrix to form a composite, it also caused a significant grain refinement of the aluminum matrix. So the grain sizes during FSP has reduced from 90 micrometer to 6 micrometer, which is a significant reduction because this is done in one step. So just one pass of FSP is sufficient, to decrease the grain size from, let's say, 90 micrometer to 6 micrometer. The percentage of grain boundaries, the percentage of high angle grain boundaries, that reduced to 55% after FSP. This is the image quality map from the same area. The purpose of showing you this is just to show that you can see a lot of pits and pores on titanium particles. So aluminum matrix was nicely polished, but the titanium face was not polished properly during electropolishing. So that's why we could not get a good pattern from the titanium particles. Now, we wanted to know, what is the mechanism of grain refinement? How does, a big grain turn into so many small grains? So how do you really, achieve 6 micrometer grain size during FSP or after FSP? We calculated the strain rate using this formula given by Chang et al. So the strain rate during the FSP process came out to be something like 112 per second. Just to give you a feel of this number, like when you perform a tensile test, uh, the typical strain rate what you use is 10 to the power minus 3 per second. So this strain rate is something, 6 orders of magnitude higher than that. Okay, so 112 per second is actually a very high strain rate. We also estimated the temperature, and the temperature was in the range of 380 to 400 degrees C. So basically during FSP, during friction stir processing, when you incorporate these titanium particles into aluminum matrix, the material is at a temperature of 380 to 400 degrees C, and also it experiences very high strain rate. Now, under the combinations of high strain rate and high temperature, this is high temperature for aluminium because melting point of aluminium is 660 degrees C. So this is like a fairly high temperature for aluminium. Now, under the combination of high strain rate and high temperature, the material actually undergoes dynamic recrystallization. So dynamic recrystallization is the process by which a big grain turns into so many small grains. Or by dynamic recrystallization process, you can decrease the grain size from 90 micrometer to 6 micrometer. The next thing we wanted to know was, now if you look at the literature, there are two types of dynamic recrystallization reported in the literature. One is called as continuous dynamic recrystallization, and the second one is called as discontinuous dynamic recrystallization. We looked at the misorientation angle distribution, and we found that the FSP material has a peak at the lower angle. That means you have a high fraction of boundaries which are having a misorientation angle from, let's say, 5 to 20 degrees. You have another hump here, so it means that you have some boundaries which are high angle. So the peak towards the left side indicate a high fraction of low angle grain boundaries, and the peak on the higher side indicates a high fraction of high angle grain boundaries. But then when we looked at the grain boundary map, okay, so this is the grain boundary map. You can see here three types of grain boundaries, which are indicated by different colors. So the boundaries which are indicated by red color, they're called as subgrain boundaries. The boundaries which are indicated by green color, they are all low angle grain boundaries. And the boundaries which are indicated by blue color, they're all high angle grain boundaries. Now here, you know, the red color boundaries means that the misorientation across the boundary is from 2 to 5 degrees. The green color means for the low angle grain boundary, the misorientation across the boundary is from 5 degree to 15 degrees. And for high angle, it is like you can say more than 15 degrees. So in this grain boundary map, you can see all the three types of boundaries. But then when you carefully look at the boundary map, You can find many grain boundaries with multiple colors. For example, look at this grain boundary. This is one boundary where you can see that this part is green in color, and this part, this part is blue in color, and this part is green in color. So it means that this part is actually a low angle grain boundary, and this part is actually a high angle grain boundary. Similarly, you can see here as well, a part of the grain boundary is like high angle, another part is low angle. And you can see, at multiple locations here as well. So this is like a low angle grain boundary. Then you have high angle grain boundary. Again, you have low angle grain boundary. Okay. You can also see mixing of subgrain boundary and low angle grain boundaries. These are all indicated by white color arrows. So here, for example, you can see this portion is green color, this portion is red, this is again green. This indicates that you actually have the boundary has a low angle character, then it has got a subgrain character, and then again it has got a low angle grain boundary character. So this mixed nature of the grain boundary, so you see mixing of these two, low angle and subgrain boundary, you also see mixing of low angle and high angle. So this actually indicates that maybe the mechanism of grain refinement is continuous dynamic recrystallization. So let's see what really happens during FSP. So we propose that the process actually involves multiple steps. So as the material flows around the pin, due to high strain rate, there are dislocations generated. Now these dislocations, which are generated within the aluminum matrix, they actually form subgrain boundary by what is called as dynamic recovery process. So this dislocation rearrange themselves and they form subgrain boundaries. Now the subgrain boundaries can increase in their misorientation by further dislocation absorption. So for example, if you have a subgrain boundary across which the misorientation is from 2 to 5 degrees, when more dislocation comes and get absorbed into this boundary, it will transform to a low angle boundary, because as more and more dislocation get absorbed into this boundary, the misorientation angle will keep increasing. So the moment it crosses 5 degree, the subgrain transform to low angle grain boundary. Similarly, so increase in the misorientation by dislocation absorption or even by subgrain rotation. So for example, if you have a subgrain which is bounded by subgrain boundaries, that subgrain can rotate. Now once it rotate, then also you will increase the misorientation across the boundaries, and then the subgrain boundary actually will transform into low angle. The more it rotates, the low angle will transform into high angle. So what really happens is there is a progressive transformation of subgrain boundaries to high angle grain boundaries. Okay, and this is actually a characteristic feature of continuous dynamic recrystallization. Now, discontinuous dynamic recrystallization involves nucleation and growth. Okay, whereas continuous dynamic recrystallization, there is no nucleation or growth. Okay, so there is a slow transformation of subgrain boundaries to low angle, then to high angle. Okay, now just the similar analysis. For example, if you look at some of the grain boundaries with mixed character, so let's measure the misorientation angle across them. So let's say if you look at this particular boundary, which is green in color. So if you measure the misorientation across this boundary, that is from this point to this point, so this particular grain boundary or this particular boundary is having a misorientation of 11 degrees. So if it is 11 degrees, it is a subgrain boundary. Now, if you calculate the misorientation at this point across this boundary here, then you found that this particular blue color boundary has got a misorientation of almost 20 degrees. So if it is 20 degrees, it is a high angle grain boundary. Then we looked at this segment, and here the misorientation angle was again around 10 to 12 degrees. So these two are again subgrain boundaries. So you can make out that we have a boundary with low angle character, then high angle character, then again low angle character. So, the low angle grain boundary, if it receives more dislocation, then actually this can transform into a high angle boundary. Okay, so this is the mechanism we propose, that there is an increase in the misorientation across the boundary by dislocation absorption or by subgrain rotation. So if this subgrain can rotate, even if it rotates in one of the direction, then this misorientation angle that is across this boundary and this boundary and this boundary will increase. Okay, we next looked at what is called as the grain orientation spread map. Now the grain orientation spread map talks about spread in the orientation. Let me write here. So this is grain orientation spread. That means we always define grain as a region of one orientation or single orientation. But then if you incorporate a lot of defects, primarily one-dimensional defect, which are like dislocations, so if you increase the dislocation density within a grain, then what really happens? The orientation, is no longer the same throughout the grain. You basically change the orientation across these dislocation boundaries. So that leads to spread in the orientation of the grain. Now, we looked at the grain orientation spread map, and then you can classify, or you can, bifurcate grains into different regions based on the Gauss value. So if the grain orientation spread is 0 to 1 degree, then those grains are indicated by blue color. If the spread is between 1 to 2 degree, those grains are indicated by green color, and so on. So the grains which have 0 to 1 degree spread, that means that these grains are strain free. It means that they have almost no dislocations inside them, or you can also say that these grains are recrystallized grains or strain free grains. Then as the spread increases, it means that these are deformed grains. So that means they have more deformation inside them. Now, we wanted to see where exactly are the dislocations located inside the grains, or what type of substructures are present in the FSP microstructure. So we carried out a detailed TEM analysis, that is transmission electron microscopy of the aluminum matrix. And when we look at the grain structure, we actually observed a lot of subgrain boundaries, or boundaries formed by dislocation arrangement within the grains. So all these regions, what you see, these are all grains. So for example, this is one grain, this is another grain, this region is another grain, and this is another grain. But when you look within the grain, we observe a lot of boundaries. So this is, for example, a boundary which is formed by dislocation arrangement. All these black lines, what you see, these are all dislocations. And we could see that, the dislocations actually have rearranged themselves into, some sort of boundaries. So here it's very clear. This region is free of dislocation. This region is again free of dislocation. And this region here, all the dislocations are like parallelly arranged. If you zoom that, you can make out that, all these lines are sort of parallel. This indicates that all dislocations have rearranged themselves to form subgrain boundary. Now, if you measure the misorientation across this boundary, so from this point to this point, if you measure the misorientation, it can be anywhere between 2 to 5 degrees. Okay, from this point to this point, because of these dislocations, there would be misorientation between this region and this region. Okay, now some of the grains, we could observe free dislocations. That means no sort of recovery. They have not really rearranged themselves, but they are like randomly, present within the grains. Okay, so the EPST results were actually supported by the TM results in proposing the CDRX as the mechanism. So here also we propose that the subgrain boundaries are formed by dislocation arrangement, and then the subgrains can rotate or the subgrains can absorb further dislocation to increase the misorientation across these boundaries. And these boundaries progressively transform into high angle grain boundaries. So that is the mechanism of grain refinement. That is, a big grain basically turns into so many small grains. Now, the next thing is we looked at these particles, the titanium particles which are added to the aluminum matrix at high magnifications and very carefully. So we observe a lot of fracture of the particles. This is a titanium particle, and you can make out that it is fractured into few pieces. And here you can clearly make out that a titanium particle is fractured into several pieces. We also looked at the titanium particles, and some of the titanium particles actually were twinned. Now, all these lines, what you see, they're all twins. Okay, I can show you another image which is at high magnification. So what really we observed is fracture of the particles and also twinning. So some of the particles were fractured like this, some of the particles were twinned like this. But then the interesting thing was this, there were more twinned particles on the rotating side. So we observed this type of particle more on the rotating side, and on the advancing side, more particles were actually fractured. It's not that we did not observe any twinned particle on the advancing side. It is just that the fraction of the fractured particle was higher than the twinned particles. The width of the twin was in the range of 0.15 to 1 micrometer. Now, the variation in the fraction of fractured particles and the twinned particles. Now, this indicate a presence of some sort of strain gradient across the stress zone. Okay, so that means on the advancing side, the strain and the strain rates are different than on the retreating side. It's actually very difficult to really quantify that in terms of numbers, that what is the exact strain rate on the advancing side, what is the exact strain rate on the rotating side. Of course, you can get some indication that yes, there is some sort of gradient, there is some variation, of course. Now, we wanted to know what really happens first, because some of the particles we observed were actually fractured and also twinned. So this particular particle, this is a titanium particle. You can see that it is fractured here, and all these straight lines, what you see, these are all twins. So here also you can see this, bright white lines. These are all twins, and you can also see some sort of cracks in the particles. So now the interesting thing comes is what really happens first. Whether twinning happened first or fracture happens first. Now, when we looked at these particles more carefully, we found that the twins were continuous on, the fractured pieces. So it means that maybe this particle underwent twinning first, because you can see this twins running from one part to other part like this, and then it underwent fracture. So when we looked at these twins at more carefully, we found a lot of cracks in the twins. So we propose that maybe the twins actually act as source of crack nucleation for the fracture of the particles. So what really happens is titanium particles, since they have a hexagon closed packed crystal structure, they have limited number of slip systems. And when they have a limited number of slip systems, they also deform by twinning. So the twins first form, and then since the twins are also region of high stress concentration, then the crack nucleate in the twins first, and then the crack propagates, and that can actually fracture the particle. So we propose that the particle undergoes twinning first, and then they undergo fracture. where the twins actually act as the source of crack nucleation. We wanted to know what type of twins are formed, so we prepared some TEM thin lamella from the twin regions. So this is a TEM micrograph of the twin titanium particle, where all these lines, you see this line, you see this line, this line, this line. These are all actually twin lines. These are all twins. So we captured the diffraction pattern from like region 1, region 2, region 3, and we found the type of twins which are present in the titanium particles. This is more like a metallurgical concept, so I'll not discuss into more detail here because what Dr. Raju told me is that most of the participants are from mechanical engineering background. Anyway, the point here is with these diffraction patterns, you can find out what type of twin boundaries are these, or what type of twins are these regions, what type of twins are formed in the titanium particles. We then looked at the mechanical properties. So we performed several tensile tests on the composite materials, and then when we looked at the properties, so the red color here, the red color curve is indicate. Sorry, the blue one is for FSP aluminum, that is a aluminum sample which has been subjected to friction cell processing without adding titanium particles. And the third black is for base aluminum or pure aluminum. The purpose of performing the test on blue sample is to see how much contribution comes, how much increase in the strength comes from the titanium particles and how much from the grain refinement. When we look at the properties, the yield strength was significant improvement in the yield strength from 35 MPa to something like 118 MPa. Now, when we compare the yield strength or the proof stress with FSP aluminum, it was 82 MPa, whereas for the composite was 118. Now, what's the difference between FSP aluminum and the composite? Nothing but the presence of titanium particles. The grain size of FSP aluminum was very much similar to that of the composite. It was again like 6 to 7 micrometer. So the improvement in strength in the composite comes from two factors. One is the grain refinement, and the second one is incorporation of the titanium particles. But then the problem comes. The problem is again the top ductility. So the improvement in strength is significant, but again, if you look at the ductility in the composite was 16% only. This is a significant drop again, but then when you compare this ductility in pure aluminum with ceramic particle reinforced composites, that is still fairly good. So if you add, let's say, 11% alumina, which is a hard ceramic particles, if you add 11% alumina to aluminum, you're going to end up getting a ductility of something like 8 to 10%. Now, when you compare that with the titanium composite, the titanium composite gave us a ductility of 16%, which is like compared to ceramic particle reinforced composite, the metallic particle gave us, you can say, high ductility with a good combination of strength as well. Now, what is the reason for improved strength and, let's say, good ductility? So we looked at the fracture surface of the composite and we looked at its particles in the fracture surface carefully. And we found that there is a very strong bonding between the titanium particle and the aluminum matrix. So these are again backscattered electron images, these two, where the titanium particles are visible in bright color or whitish color. So if you look at the interface, you can clearly make out that the titanium particle is trying to pull the aluminum matrix. So this indicates that the bonding here is very, very strong. And here also you can make out that the aluminum matrix is very nicely bonded to the tiny particle. So after performing a tensile test, this is our tensile specimen. My mouse has great problems. Okay, tensile test specimen, and this is the fracture surface. So this surface, the images are given here. And when we looked at the surface, we found that the tiny particles were actually having cracks inside them. Then we did not observe crack at the interface. So this means that the interface between the tiny particles and matrix that is strong. And the particles are actually strength compared to pure aluminium. But then when the crack propagates through the particle, it means that the interface is very strong. The interfacial bonding to the aluminium matrix and actually the good interfacial bonding. Just to tell you, we do not get this type of bonding when you add ceramic particles as reinforcement. Okay, so when you add ceramic particles, you're not going to get a bonding like this. Okay, so the next thing what we did is, so as I've told you at the beginning, these are non-equilibrium composites. What we mean by non-equilibrium is, these composites are sort of unstable. So if you expose them to high temperature and go towards the equilibrium conditions, what's going to happen is they're going to go towards equilibrium. That is, if you look at the phase diagram of aluminum and titanium, they have to react and they have to form some stable metallics. So we wanted to know the thermal stability of these composites. The thermal stability in terms of two aspects. One is the microstructure, that is, during FSP we get fine grained microstructure. Now that particular fine grained microstructure, is it stable at high temperature first of all? And if it is stable, up to what temperature it is stable? Because if you want to use this composite at high temperature, you should know the stability of the microstructure at high temperature. So let's say at high temperature, the microstructure is not stable. It undergoes some sort of grain growth. So when the grain size increases, what's going to happen? The material's strength and hardness going to drop. So we did a series of heat treatment to find the stability of the microstructure. So we found that the microstructure was actually stable to a temperature of 400 degrees C. We subjected the sample to 400 degrees C, and for 10 minutes it was stable. At 400 we checked up to 1 hour, there was no grain growth. So these scans are taken from the same area. So the particles what you see, these are all tiny particles, 40 degrees C after 10 minutes of exposure. So we found that again these scans are in the same area, so there was a huge grain growth. We call this as abnormal grain growth. So we found that some grains grew very, very large and very fast at 440 degrees C. Then we continued the heat treatment, and at 440 degrees C we found that the grain was actually very, very large. So all the fine grains, they were consumed by the bigger grain of green color, and then you're getting like a very, very large grain size. So here, for example, everything appears green in color. That means this is one particular grain having orientation of 101. This happened at a temperature of 440 degrees C after 20 minutes of thermal exposure. So all these scans are like in the same area after a sequence of heat treatments. Between every heat treatment, we quench the sample, and then we took it to SEM and we performed this EBSD scan. So what we can see here is there is abnormal grain growth. Now, if it is a normal grain growth, then the grain size increases, sequentially your grain size distribution slowly shifts to, larger sizes. But during abnormal grain growth, certain grains grow very, very fast. Okay. The concept of abnormal grain growth is very useful if you want to, get a large grain size material, or let's say you want to generate a metallic single crystal. Okay, so here we performed a large area scan. We just wanted to see, what the actual grain size. So the scan size was 4 millimeters into 400 micron. So from this end to this end, that is the length of the scan is 4 millimeters, and the height is 4 micron. You can see that this particular grain, which is in green color, this is huge. This is like really, really big. It is of the order of, I would say, almost 3 millimeters. So if we can generate a grain size of the order of few millimeters in solid state, it's a new thing. It's always good, because it's not very easy to make metallic single crystals by within solid state. Because if you look at a normal grain growth, even if you take a metal example to a temperature which is close to its melting point, there will be grain growth, but then the grain growth stagnates. Okay, the grain growth always stagnates, and whatever you do, however high temperature you take, the grains will stagnate. The growth will stagnate after some time. So you cannot achieve a grain size typically larger than, I would say, 500 micrometer. That's half a millimeter. But the friction process microstructure is actually good if you want to achieve a grain size of few millimeters. So then you can generate single crystal, which are like few millimeters big at least for certain applications, by taking a aluminum sample, doing FSP on that, and doing a heat treatment on it. If you do it heat treatment at 400 degrees C for 2 hours, you will end up getting a very large grain size material. We did the same scan on the composite, for example, and here you can see all this all black green at all. I mean, these are all like one color, all one. So the grain size is of the order of few millimeters. After heat treating the temperature, the particles are stable. So in the first case, we wanted to see the stability of the microstructure, and in the second case, we wanted to see at what temperature the particles are stable, because these particles are actually in non-equilibrium condition. So if you expose the composite to very high temperature, they're going to go towards equilibrium. That means they're going to react with the aluminum and they're going to form intermetallics. So we subjected the composite to again a series of heat treatment at high temperature, and this time we monitored the titanium particles carefully. So this is the image of the titanium particle. This is our aluminum matrix, and this is another SEM image taken after centigrade. Okay, so at this temperature, we found that titanium started to react with aluminum. So this is like before the heat treatment, that there is sort of a thin layer formed around the particles. So you can see that in other figure as well. That is, these are the titanium particles, and at a temperature of 5 degrees for 20 minutes, the particles started to react with aluminum. Okay, if you look at the interface high indication, and then you can make out that this thin mapping, not mapping, elemental line scan across this interface. You can see that this particular region is rich in both aluminum and titanium, indicating it is forming some sort of reaction product. Titanium composites. The next key thing is in the next study we choose copper as reinforcement. Okay, at this point, what I would suggest is, can we take a short break here for 5 minutes? Uh,
Yeah, sir.
Dr. Raju, is it okay? The candidates may
Is it okay, sir? Is it okay? So this is Amit Kumar speaking. So so I'm the one of the coordinator for this thing.
not need a break.
Sir, it's okay for five
Is
minutes.
it
It's
okay?
okay, sir. No problem. You-
Sure. Okay.
Okay, sir. Thank you. Hello, sir. Hello, sir. Devendra, sir.
Yes.
Sir,
Yeah.
your voice is pausing in between for a certain time, for certain seconds, and then it is like rapidly opening up. So there's some delay, delay in voice.
Right. I understand that. I mean, this is always a problem with the internet
Internet,
here.
yes, I think internet problem.
Let me see what best I can do. So
Okay,
give
sir.
me
Okay,
five
sir.
minutes.
Yeah.
Right. Let me change the connection then.
Okay. So, okay, dear participant, we will meet up to 5 minutes break.
The number you have dialed is invalid.
Hello, sir.
Yeah. Yeah, Dr. Raju, we can start again.
Yeah, sir. Okay, sir. So we'll
Okay.
continue, sir.
Yeah, I've changed the connection. Let me see how it works. I'm
Yes,
not
sir.
sure it's going
It
to
is
improve.
coming. Sir, it is coming continuous. No problem.
Okay, let's see.
Yes, sir.
Okay, just let me know if you can see the slides.
Yes, sir. It is visible. It is
Okay.
visible.
Okay, everyone. So let's start once again. So this is what we discussed already. Now, so in the next case, what we did is we used copper particles. Now, if you look at the morphology of the copper particles, this was actually more or less like spherical particles, which is different from that of the titanium particles. In the case of titanium particles, the particles were actually, irregular, and we had a wide grain size, wide particle size distribution. In the case of copper, the particle size distribution was narrow, but the average particle size was quite big. It was around 70 micrometer. So we, adopted the same methodology. What we did is we used pure aluminum plate. We made a groove on the aluminum plate and then filled the groove with the copper particles. And after that, we carried out FSP or friction stir processing on the plate. And then what really happened was the copper particles actually got uniformly distributed in the aluminum matrix. So when we did the XRT of the composite, again, we got peaks of aluminum and copper. Now, if copper goes into solid solution of aluminum, what would happen is you will not observe copper peaks because copper would actually dissolve into aluminum. So in this case also, copper did not really dissolve into aluminum and it was retained in its elemental state. So if you look at the SCM image of the composite, then you can see that all these, bright particles are copper. This is a again backscattered electron image, where since the atomic number of copper is higher than that of aluminum, the copper particles appear in bright color. We looked at the particle matrix interface.
Hello, sir.
This is one copper particle in the aluminum matrix, and if you look at the interface, yes, there are
Sir,
still problems.
sir, sir, can you make it full screen? But it's showing a slideshow. So maybe so not the full
Oh
screen.
my god!
Yeah.
1 minute, 1 minute. Uh, okay, give me a minute. Why?
Slideshow, you can make it, sir.
Okay.
Okay,
Is it
sir.
fine now?
Yeah, sir. It is completely full screen. Okay.
Okay. Oh, sorry for that. Right. So here you can look at the interface of the copper particle and the aluminum matrix. So here also we observe a clean particle matrix interface. That means there was no sign of any dissolution of the copper particles in the aluminum matrix. So here also we can say that by FSP process, we have retained the copper particles in their elemental state within the aluminum matrix. But again, this is a non-equilibrium composite because under equilibrium conditions, copper would actually dissolve into aluminum and it would form a solid solution. We looked at the elemental distribution through EDAX mapping, and here also we found a uniform distribution of the copper particles within the aluminum matrix. So here the copper particles are indicated by red color and the aluminum matrix is indicated in green color. So this is again a non-equilibrium composite. We looked at the microstructure through EBSD, that is electron back scattered diffraction. And in this case also, the average grain size what we got in the aluminum matrix was 5 micrometer. This is exactly same what we got for titanium particles in the case of aluminum titanium composite. It's not really related to the reinforcement what you use. The average grain size is actually related to the processing parameters. So since our processing parameters was same, that is our tool rotation speed was 1000 RPM and the traverse speed was 30 millimeter per minute in both the cases. So since the processing parameters were same, the strain rate and the temperature was same. And that's why the average grain size was same for aluminum titanium composite and aluminum copper composite. Remember, grain size is for the aluminum matrix. Now, in this case, the percentage of grain boundaries were actually much higher. It was 83%. So this was like a well annealed type of microstructure. Now, the reason for that is in case of titanium, we had a wide particle size distribution. We had some very small particles and some very big particles. So those, when you have a wide distribution of the particle size, when they flow with plasticized aluminum, they generate a lot of strain in the matrix. So that leads to a lot of dislocation generation, and because of the large number of or you can say high dislocation density, then you're going to get a lot of subgrain boundaries and low angle grain boundaries. Whereas in the case of copper, the copper particles were actually significantly larger. They were significantly bigger, so they do not really affect material flow behavior. So that's why you get high percentage of high angle grain boundaries. The grain size distribution was narrow in this case. So first of all, again, there was a significant grain refinement because compared to the base aluminum or pure aluminum, which had a grain size of 90 micrometer, after FSP, the average grain size decreased to 5 micrometer. And it is significant since there's a huge decrease in the grain size. The second thing is, this is achieved in just one step. So if you look at most of the grain refining techniques, what you need to do is you need to carry out several passes, or you need to perform the same step several times to get a fine grain size. Whereas by FSP, you can significantly reduce the grain size in just one pass of FSP, that is in one step. Now the grain size distribution was narrow. That means most of the grains, 80% of the grains were in the grain size range of 3 to 9 micrometer. So when you have narrow grain size distribution, this is going to give you uniform mechanical properties within the material. So more than the average grain size, it is the grain size distribution which is important to get uniform mechanical properties. Okay, for the composite, again, when we looked at the mechanical properties, there was a good improvement in the yield strength from 35 MPa of the base metal after FSP. The strength increased to 88 MPa. And in this case, now the composite exhibited a good amount of ductility. The reason for this also is that copper itself is actually very, very ductile. When you compare that with, let's say, even aluminum or even with titanium in the previous study. So you get good ductility because the reinforcement particle itself are very, very ductile. Now here also, when we looked at the fracture surface after the tensile test, we observed the particles were actually nicely bonded to the aluminum matrix. And here also you can make out, aluminum matrix nicely coating sort of, on the core particles. So the interfacial bonding is again very, very strong here. Now the next thing what we did is we wanted to look at thermal stability. Again, two aspects. One is the thermal stability of the microstructure, and the second one is thermal stability of the copper particles. So when we studied the thermal stability, when we were doing experiments to see up to what temperature the particles are stable, In the case of copper, we found that the particles were stable up to a temperature of 350 degrees C only. At 350 degrees C, after 10 minutes of thermal exposure, some reaction began. So I'll show you a few images which are taken at different steps. So this is the microstructure at a particular location in the composite for the as process composite. What you see here is these particles, the particles, what you see in whitish color, bright color, these are all copper particles. So you can see a gap between the copper particles in the as process condition. Now, when you subject the composite to 350 degrees C for 10 minutes, some sort of reaction happen. That means copper start to react with aluminum matrix. At 350 degrees C, when you keep it for 30 minutes, then you see some sort of layer forming around the copper particles. So now you can see the gap between the particles is reduced. Right here, there was a significant gap between the two copper particles. And then if you, when we left the composite at 350 degrees for 120 minutes and then looked at microstructure, then these two copper particles were sort of bridged. Now, what does it indicate? It indicates that actually copper is coming out of the particles. Copper atoms are diffusing out of the particles, and it is reacting with the aluminum matrix, and it is forming some sort of reaction product. So if copper is coming out, copper atoms are coming out, then what is left behind is some sort of vacant site or vacancies. Now these vacancies actually can condense and they can form some pores. If you look at this image carefully, you can make out a lot of black dots here. These black dots are actually pores. Okay, so what we are getting at is basically a core shell type of microstructure where the core is, let's say, pure copper, and the shell is nothing but a intermetallic of aluminum and copper. So when we did EDS elemental mapping, and there's a new feature in EDS which is called as phase mapping. So when we did the phase mapping, we found that there were actually three phases present. The phase which is in red color contained only aluminium. The phase which is present in blue color contained only copper. But the phase which was present in yellow color, that contained both aluminium and copper. So there was a reaction between aluminium and copper. So the point here is that these particles are actually unstable beyond a temperature of 350 degrees C. So you can effectively use this composite, let's say, at a temperature of 300 degrees C. If you go 350 degrees C, there is every possibility that after a certain time, aluminum and copper would react and they would form some sort of intermetallics. Now, I must tell you that in this case, the abnormal grain growth, that happened only at 440 degrees C. So in the case of aluminum titanium composite, titanium particles were stable up to 550 degrees C. Whereas in the case of aluminum copper composite, the copper particles are stable only up to 350 degrees C. The matrix, the microstructure of the matrix aluminum, that was stable up to 440 degrees C. Beyond 440 degrees C, it underwent abnormal grain growth. This is just another, images which you can see that this is before the reaction, before the thermal treatment, and this is after the thermal treatment. So you can make out here that the interface is clean, and after a thermal exposure at 350 degrees C for 10 minutes, now you see some sort of reaction happening. So, and now you can make out a lot of very fine pores on the copper particles. So these pores basically are forming because copper atoms are diffusing out of the copper particles and then reacting with aluminium. And then if you continue the reaction for 30 minutes, then you can see some sort of reaction layer around the copper particles. And you can see some large pores on the copper particles. So this is the same thing, I mean, just like in the previous slide, but monitoring a portion of the particle matrix interface. So, it's the same interface which is shown here. So before the heat treatment, It was clean, and after the heat treatment for 120 minutes at 350 degrees C, you can see some sort of reaction for happening. And now you can see a lot of big pores. The pores are formed because copper atoms are going into the reactor in the aluminum matrix. When we looked at this region carefully and when we tried to look at the elemental composition, we found that the chemical composition was very close to Al2Cu for the outer ring, and for the inner ring it was like AlCu. So basically the shell, the core is still copper particle, but the shell composed of two different reactions. And then this is again the elemental mapping, where this blue color indicates pure copper, red color indicates pure aluminium, and the yellow color phase, it is actually rich in both copper and aluminium. So the elemental mapping, what you see here is from the yellow color phase, that is this region. That is rich in both aluminium and copper. Now, thermal stability. So in this case, the AG happened at 400 degrees C, not 440 degrees C. So the abnormal grain growth happened at a temperature of 400 degrees C after 10 minutes of thermal exposure. So the microstructure is stable up to a temperature of only 400. Above 400, you can say even at 10 minutes of thermal exposure, then you get abnormal grain growth. That means certain grain grow very, very fast. And if you continue the heat treatment, that is at 400 degrees C, if you leave the sample for 30 minutes, now you get like very large grain size. And if you increase the time, make it like 2 hours, then probably you'll get like everything in one color. That means a very, very large grain size of the order of few millimeters. All these scans are performed in the same area. So what you see here with black color, these are all copper particles, and they were all like spherical particles. Okay, then we wanted to see a little more detail what really happening during abnormal grain growth. So this is the microstructure of the base composite, that is as processed condition. And then this is the same microstructure somewhere in this zone. This is zoomed here, and you can see now some grains trying to grow abnormally, that is trying to grow very, very fast. For example, this grain, which is in bluish color, now it absorbs all these neighboring grains, and it grows like this. It grows bigger. And then if you continue the heat treatment, this will probably be absorbed by some other grain, and then the orientation grows very fast. So in the case of aluminum copper composite, the abnormal grain growth happened at a temperature of 400 degrees C. But the particles were not stable at 400. The particles started to react with the aluminum matrix at 350 itself. So the microstructure was actually stable at 350 degrees C. We checked only up to a temperature only up to 120 minutes, that is of 2 hours of thermal exposure. There was no grain growth. So the particles were stable up to 350 degrees C in this case, and the microstructure was stable up to a temperature of 400 degrees C. Well, now we can conclude this work. So these are the conclusions. So we can say that FSP, that is friction stir processing, it can be used as a tool to incorporate metallic particles into aluminum matrix, and thereby you can produce non-equilibrium composites. So FSP, it's doing two things. It not only incorporates the metallic particles into aluminum matrix to form a composite, but it is also causing a significant refinement of the aluminum matrix. And we get equiax fine grains. The microstructure of the matrix aluminum, that is characterized by equiax fine grains with a high fraction of, or you can say good fraction of high angle grain boundaries, and with narrow grain size distribution. Narrow grain size distribution is very important if you want to have uniform mechanical properties in your material. There are multi-mechanisms which operate during the grain refinement process, that is dynamic recovery and continuous dynamic recrystallization. The interfacial bonding between these metallic particles and the aluminum matrix was very good, and that actually improved the mechanical properties. Now, during FSP, the aluminum matrix that underwent abnormal grain growth at a temperature of 400 degrees C, and after incorporating the titanium particles, the aluminum titanium composite that underwent abnormal grain growth at 440 degrees C. Now, this particular microstructure is suitable for producing metallic single crystals. Of course, you not produce very large metallic single crystals of the order of, let's say, few centimeters, but at least a few millimeters for certain applications. When you want small metallic single crystals, maybe FSP microstructure can be explored more. Now, the titanium particles were stable up to a temperature of 550 degrees C, and the copper particles were stable up to a temperature of 350 degrees C only. So efficiently, you can say that there is a temperature limitation up to which you can use this composite at high temperatures. If you go beyond those temperatures, then you may have problems. Now, this metallic particle, they produce or they form a diffusion couple with the aluminum matrix, and then when they react with the aluminum matrix, they form the stable reaction products, and this happens due to what is called as the Kirkendall effect. Kirkendall effect means when the atoms move in one direction, the vacancies move in the opposite direction. So when the atoms move into aluminum to react with aluminum, the vacancies they cluster within the particles and they form what are called as now pores. Okay, so with this, I can thank all of you for patiently listening to this talk, and well, now we can have discussion. I think we have got good time for discussion. So if you have any doubts, any questions, you can ask me. You can also type your questions in the chat box if you want to.
Dear participant, if you have any queries, so that you can ask now.
Yeah, let me go to this mode so that I can look at the chat box and so let me go to the beginning. Yeah.
Dear participant, if you have any queries, you can
Like
ask.
everyone is,
So,
yeah, look like everyone is hungry for lunch.
yeah, sir. So here one of the participants is asking what is the application of FSP. It is from Karuna Singh.
Okay, so yeah, I mean, you can use FSP for several applications, starting from, let's say, you want to just refine the grain size of your sample. Okay, so this is something like very easy
Yes,
technique. You
yes.
can always achieve a good amount of grain refinement in one step. That is one application. Second application is, let's say you want to refine the microstructure of your material. This is very useful when you're dealing with cast products. So when you take any metallic casting, it will always have a lot of casting defects, such as porosity. You'll have the dendritic microstructure. You'll have some elemental segregation. You'll also have some pores. So if you subject, this cast microstructures to FSP, the FSP would break all these, dendritic microstructure, and it will give you a very homogeneous microstructure. So it will remove all the casting defects. That is second application. The third application is what we spoke. I mean, what I presented here. You can also use FSP to prepare some composites. So in this case, we have used metallic particles as inputs. But you can always use even ceramic particles. People have used even like nanomaterials like car nanotubes and same to incorporate into some metallic system to prepare composites. And these composites actually, you can use it anywhere.
Hello, sir. There is one more query. Like
Yes, you can.
it is used only for metallic materials.
Yes. Yes, that is the, well, you can say fortunate or unfortunate thing. I mean, because metals are ductile. So if you subject this FSP to ceramic materials, it is not going to work because your ceramic materials are brittle. Of course, you can use ceramic materials as reinforcement into aluminum matrix or any other metallic matrix by FSP. But yes, it works very well for metals. It may not work even for some of the metals, like, it's very tricky to do FSP on titanium. There are many reports, but I would say it's not a straightforward thing. So it doesn't mean that even all metallic system it's going to work. The metallic system which are like very very, you can say very, or the metallic system which are, let's say, less ductile, or they have a HCP type of crystal structure, there the problem comes. For FCC based metallic systems, it's very easy. People have successfully carried out FSC on aluminum, copper, nickel, austenitic steel, things like that.
Okay, sir. Thank you for your wonderful session, sir. It was very much informative for the participant, and hope it is going to help for the future work, for the research as well as for their enhancing the knowledge. So thank you, sir. Thank you, Devendra, sir. Thank you.
Yeah, sure.
Dear, dear participant, we'll going to meet at 2:30 again for the next coming sessions. So till now we have so we have a lunch break here. Thank you everyone. Thank you.
Hello. Hello.
Hello, sir.
Sir.
Sir, shall we start a session?
Yeah, please, sir. I
Yeah.
will share the screen.
A warm welcome to everyone. Welcome to afternoon session of day one. So I would like to introduce our beloved speaker for the session, Dr. Ramesh MR. Dr. Ramesh MR completed his BE Mechanical Engineering from Siddhganga Institute of Technology, Tumkur. He completed his MTech in Mechanical Engineering with a specialization of Manufacturing Science and Engineering from MS Ramaya Institute of Technology, Bangalore. He is awarded with PhD from Indian Institute of Technology, Roorkee, with his thesis title Studies on the Role of HVOF Coating in Improving Resistance to Hot Corrosion and Erosion. Currently, he is working as Associate Professor in National Institute of Technology, Surathkal, Karnataka. Currently, his area of research include thermal spray coating, thin films, laser and microwave surface modification, biomaterials, machining, wear, erosion, oxidation, and hot corrosion. As he has published n number of journals and reputed journals in national and international level. So, with this small introduction, I would like to hand over the session to Dr. Ramesh MR. Sir, over to you.
Yeah. Thank you, sir. So I will share the screen. Please see just.
Dear participants, if there is any queries, please put it in the chat box. The speaker will be addressing on that at the end of the session. And the feedback link will be shared to you at the end of the session in the chat box, as well as it will be sent to you in the WhatsApp group. Thank you.
Yeah. Are you able to see the screen in
Yes, sir. Yes, sir.
Full screen mode? Yeah. So I am going to talk on role of thermal spray composite coatings. So generally to resist the surface degradation. Okay. So the surface engineering, it deals with the modification of the near surface structure or the chemistry or the properties of the surface to resist the surface degradation. Okay. So there are various surface damages. It may be a chemical attack due to the acids, alkali, and salts. Okay, or it may be due to a thermal effect when the component is exposed to a direct flame or very high temperature or the arcing. So once it is exposed to high temperature, so the oxidation is the phenomena. So along with that, so if there are salts, corrosive species present in the environment, so it may lead to a kind of high temperature corrosion or various other kind of degradations. And there may be a multi-component gaseous salt environment or the hard particles which may lead to a kind of mechanical kind of damages like wear or a erosion or a friction. So the erosion, it is a progressive loss of a material due to the interaction of the surface with the impinging fluid or a solid particle. And wear, it may be a surface interaction in close proximities. Okay. So these are various surface damages generally occurs in industrial environment. Okay. So the solution to such surface damages lies in different fold. So one is by changing the surface metallurgy. Okay. So we will improve the surface metallurgy in order to bring resistance to the wear, fatigue, or or to relieve the stresses. So generally the method used is surface hardening or laser melting. Okay. So or the short peening to introduce the compressive stresses on the surface. Okay. So this is the first fold. And the second fold is by changing the surface chemistry. Okay. So it may be a popular methods like carburizing. So where we will diffuse the carbon onto the steel surface, generally the ferrous surface, okay, ferrous metals. So then you will subsequently you can go for a conchin to get a very hard phase like martensite and all, or the nitrates or the borides, okay. So that is by changing the surface chemistry, or even you can prepare the composite surface by alloying, okay. You can locally melt using a laser, and you can introduce some of the hard phases on the surface, or ion implantation, okay. So you can implant some of the elements onto the surface to change its surface chemistry. Maybe it may be for a kind like even semiconductors. It is produced by ion implantation, or you can get a friction and wear resistant surfaces and all. And the third flow level is by adding a surface layer or the coating, okay. So there are various methods of coating. So it may be thermal spray coatings, okay, or the electroplatings, or a layered means vapor deposition, okay. It may be physical vapor deposition or the chemical vapor deposition, okay. So today my talk is on the surface coatings to produce a composite surfaces, okay. So the coating, it is means it is a layer formed on the material surface, okay, in order to improve the required properties. We can tailor made the surface to combat the various degradations like abrasion, erosion, wear, fatigue, oxidation, and corrosion, okay. So it is basically a tailor-made surface, okay, and and it will protect the substrate from various surface degradations. So when you are adding a external layer or a surface layer, okay, so there are the one thing which we should consider is the thickness of the layer to be added, okay. If you need a very thick layer, okay, basically this coatings are sacrificial in nature. So if they okay, so it may be if you need more than 1 mm of thickness, generally we go for this PTA or weld hard phase or a cladding, okay. And suppose in the range of 300 to 500 microns, generally we choose a method called a thermal spray coating, okay. And if it is less than 1 micron, okay, so or in the nanoscale, then generally we go for vapor deposition, okay. And we don't want to alter the surface, okay. We don't want to add the layer at all, okay. You can alter the surface chemistry mainly by nitriding at all, okay. So these are the various okay technologies we can use. Okay, so before going into my work, I just want to brief about some of the areas on which we are working on at NITK. Okay, so we are basically developing a surface coatings using thermal spray method, vapor deposition method, and microwave claddings using laser or a microwave. Okay, so this is we develop these coatings for various application. One such application is it can be used coated on a furnace walls or a superheated tubes or a reheated tubes in a power station boilers. Okay, so these are some of the coatings which we have developed. Okay, these are all the composite coatings. We so the metallic matrix or the alloy matrix will be modified by reinforced by some of the carbides or the oxides. Okay, so these are some of the composite coatings which we have added basically to for the applications in power station boilers. And these are some of the publications which we have published in some of the journals. Okay. And also these coatings which we have developed for power station boilers, we also tested at one of the superheater zone of coal-fired boiler, okay, in Guru Gobind Singh thermal power station. Okay, so we kept those coatings, coated samples in a superheater zone. So and every 100 hours of exposure, we would measure the thickness loss as well as surface damage, okay, weight loss, okay. So and some of the coatings like NICR, FESIB, it really give a fairly a good result, okay. Otherwise, if the surface of these boiler tubes are not maintained well, it may lead to a thinning like this, and then it may lead to a catastrophic failure. Okay, so the coating is coating using thermal spray technology. So it is very, the on-site application is much more important, and this can be achieved by thermal spray technology. This is how you just need a gas cylinders and a gun. You can put the material whatever you want onto the surface to maintain the tubes. Okay, and we also develop some of the cermet coatings. These are some of the cermet coatings, okay, on turbine blade alloy. Okay, basically to improve the generally the thermal barrier coatings are used. This can be replaced by the cermet coatings, okay, to in order to improve the toughness. And we also develop some of the coatings for basically for adhesive wear application. We have added a solid lubricant. Okay, the solid lubricant, maybe some of the solid lubricant work well, very well at high temperature, and some of them work very well at low temperature. If you combine both of them in a single composition, so the range of its operation can be a wide range of operation can be achieved. Okay, so these are some of the coatings which you have developed by combining the composite coatings with the solid lubricants like MOS2, CIF2, okay, and all. Okay, and these are some of the publications. And we also modify the surface of magnesium zinc rare earth alloy, magnesium alloy, using a lens, okay, for basically for a bio application. Okay, so and also we carried out cytotoxicity and in vitro degradation aspects and all. Okay, so laser is also lens is also a method to improve the surface of biomaterials like magnesium. Okay, so and we also have facilities like cathodic arc evaporation and magnetron sputtering, so vapor deposition technique. So these are some of the coatings basically for tool application, cutting tool application. We coated on cutting tool inserts, and we studied the machinability of various art to machine alloys. Okay, and these are some of the publication out of it. And recently we developed a partially oxidized coating. So we combine, means what we did is we have taken a powder, metallic powder, we flame spray onto a tub of water. So when you flame spray into a tub of water, the surface of the powder will get oxidized, and the core of the powder will be in a metallic state. So that will provide the toughness, and outside layer will be very hard. Okay, so and once we get these kind of partially oxidized powder, that can be sprayed onto the surface, okay, of the component using a plasma spray or HVF method. Okay, so and also for the wear application, we have developed some of the coatings like high entropy alloy coatings. Okay, so so these are COCR, NI, MOTI. This is what we have developed, and we mix all these elements in equal proportion. Okay, So and then we process it using a microwave. Okay, so this is also for a wear application. And some of the work on cladding we done using a TIG, okay, as well as the microwave. Okay, so and so these are few of, and also we develop a composite layer using a cumulative roll bonding process. Okay, so and these are some of the publication out of it. And so these are some of the work which we do basically on developing a composite coatings. Okay, and we use a method called I am going to talk on thermal spray coating basically now in this talk. So these are okay, so the powder will be heated, okay, using a thermal energy and then sprayed onto the surface. Okay, so it will produce a most protective oxide layer when you expose to a high temperature, or if one layer is degraded using a combined effect of erosion or wear or any surface degradation phenomena, so the next layer will heal up. So we call it as a self-healing type. Okay. One second. And it will maximize the efficiency of the plant. Okay. And cost to performance, it will always be less. Okay. And some of the example of surface damage at high temperature in the industrial environment are where these kind of coatings are used are. So accelerated high temperature fire site corrosion associated with the presence of molten alkali containing salts of superheater and heater tubes. Okay, and then erosion of combustion turbine component in dusty environment like expanded turbines in pressurized fluid bed combustors. Okay, the rollers, hot working punches, heat exchangers of steel making plants, and also the piping in petrochemical industries. Reformer baffled plates or the tubes in fertilizer plants. Okay, or even nuclear parts like feed wall, combustion chamber, and all. And even in the components of ISC engines like large size piston rods, high temperature springs, and all can be coated. And industrial waste incinerators, chemical and food processing equipment, ship propellers, and in a few components of aircrafts like windshield, wings, propellers, and rotors. Okay, so these are some of the application. So the entire application can be divided into five kind. One is the coating can be developed as a conductive coatings. Okay, so which will conduct the heat across the coating, or it may be a thermal barrier coating like in IC engines. Okay, so it is these coatings will act as a barrier to the flow of heat. In conductive coating, like in boiler tubes, we need to conduct the heat across. Okay, or the functionally graded coatings. So the composition vary from one end of the thickness to the other end. Okay, so it may be in a layer wise or in a progressive wise. Okay, next is the composite coating or the cement coatings. Basically we are developing these kind of composite coatings, or the amorphous or a bulk metal glass coating. So nowadays for a biomedical application, people realize that amorphous structure is much more advantageous than the crystalline structure, because it can exist in a body fluid in a better way than the crystalline structure. Okay, so the coating types of thermal spray process. So there are four different types like flame spray, plasma spray, HVOF, and detonation gun. Okay, I will explain, give a glimpse of these process. So this is high velocity axial process. So as you see, so as the name itself says, so the oxygen, the fuel will be burned with the help of the oxygen, and then it will be propelled, okay, at a very high velocity, okay, using a nozzle, okay. So the fuel will be burned in the presence of oil in a combustion chamber, then it will be expanded to a very high velocity using a nozzle, okay. So you can see this process, how the coating get deposited. So this is the gun. So the schematic, the gun is given here. Okay. So here, so the powder will be okay. So the bonding mechanism will be mainly by mechanical interlocking or the mechanical interaction. So the meaning of it is, so before we deposit the coating, the substrate will be made rough. Okay. So the surface will be made rough, and once the powder splat, okay, impact on the surface, so it will lock mechanically to the substrate, okay. So that we call it as a mechanical anchoring, okay. Or there will all since it is heated in the combustion chamber, so there will be a local wetting also, okay. So the local welding as well as mechanical interlocking are the phenomena in which these coating get bonded to the substrate. So this is how the coating look like. So it is a dense laminar structure, okay, and generally the thickness will be between 250 to 300 microns, and the porosity achieved in this process will be always less than 2%, okay. So the main advantage of this HUF process is you can produce a homogeneous and a dense coating with a better bond strength and interparticle cohesion. So the porosity will be very low, and since we are not melting the powder particles, so there is no limitation on coating material, and since the retention time of these powders in the flame is very less, so there will be less degradation of the powder, and metallurgical property of the substrate remain unchanged, okay. And you will get a unique microstructure, means a laminar structure you will get. So that will be very advantageous in a corrosive environment, because the corrosive species generally diffuse through the splat boundaries. So if you increase this boundary, okay, so the time with which it reaches the substrate and degrade the substrate will be extended, okay. And you can get a wide range of coating thickness, okay, by controlling the number of passes, okay. And on-site application and repair of component is the major advantage of this process. And also the other coating process are limited by the size of the component, but here there is no limitation in the size, and cost to performance ratio will be very low. And to this family, the one more method is detonation gun process. It is similar to HUF. You can see the process here. So it is similar to HUF process, but here there won't be there will be a detonation, okay, pulses or the impulses, okay, which will be created using a spark plug, okay. So there will be sparking occurs, around 5 to 7 sparks occurs per second, and it will be the impulse or the spark, okay, will carry the powder and it will get deposited onto the surface. Next is the plasma spraying, okay. So you can see the process. So in this an electric arc, okay, it will be started with a very high frequency spark, so which is the energy source for plasma spray. So into this arc, okay, gases such as argon, helium, nitrogen, hydrogen, okay. So they can be used, okay, and then mixtures are introduced. So so there will be a reaction between electrons from the cathodic source and the gas molecule. It will cause a dissociation or the ionization of the gases, okay, and this create a plasma state, and they will be expanded radially and axially and accelerated through the nozzle exit, okay. So generally the temperature of the core of the plasma, it may exceed more than 20 to 30,000 degrees, okay. So and the spray powders are usually injected into the plasma jet through a small tubes, okay. So this is the plasma spraying process. And other than that, when we look into the vapor deposition, it may be physical vapor deposition or chemical vapor deposition. Physical vapor deposition means, so you will get a vapor, okay. So by providing the thermal energy to the target, so we'll get a vapor. That vapor will just get deposited on that substrate material, which are this is a line line of sight process, okay. So the target as well as the substrate will be kept parallel, and it will just go on deposited one above the other, okay. So it is something like in the morning time you may see the water means water vapor in the atmosphere. They will get condensed onto the leaf, okay, and you will see a water droplets on the leaves in the same way. So the vapors of the target material will get deposited. We call it as a thermal evaporation. And sputtering, so we can use some electron stream, okay, to sputter the atom or the molecules from the target material, and they will go and sit on the substrate. It is something like, suppose if there is a heap of stone, if you throw a stone onto that heap, okay, what it will do, it will dislodge some of the stones at the same moment, okay. So in the same way, the sputtering, the combination of this thermal evaporation and sputtering, we call it as ion plating. Next is the chemical vapor deposition. So here also this is also a vapor deposition where in which, so in the vapor state there will be some chemical reaction which may lead to the formation of some compounds or the oxides, okay, or the intermetallic. So and it can be deposited in the same way, okay. So once these coatings are deposited, so sometimes it demands the post coating treatment. So post coating treatments like laser remelting or the furnace heat treatment, ion beam treatment, and microwave treatment. So we are having a microwave treatment unit in our laboratory. So we just convert this a domestic microwave into a microwave which is required for remelting of our coatings. Okay, so this is done to homogenize the structure of the coating, or sometimes to induce the oxide layers, which increase the wear and corrosion resistance of the coating, or the interconnected network of voids and oxides at the splat boundaries will be destroyed, and the corrosion resistance of the coating can be significantly improved. Okay, and it also increase the coating adhesion strength. So once these coating and post coating treatments are carried out, so one has to characterize these coatings with respect to microstructure, residual stresses, bond strength, okay, or the fracture toughness, and the phase composition. Okay, so there are different levels. So I just want to give a brief on this characterization. So there are different levels of structure property, means internal structure examination. Okay, because the behavior of material is closely related to the properties of the material. Okay, so there are different levels. One is the microstructure, wherein which you can use optical microscopes. You can magnify up to around 1500 times, and you can see the features. The second level is substructures. Okay, so substructure of material means still lower level. Means you are able to resolve to a few tens of Armstrong. Okay, so these are the electron microscopes. So it may be a scanning electron microscope where you can scan opaque material and the depth of focus is high, or it may be a transmission electron microscope where material used here is very thin and to the extent of fraction of microns. Okay, so and okay, so this kind of substructure examination through the electron microscopes. Okay, so they actually, okay, so bring about lot of research in materials science. Suppose say, to just give an example, suppose say in 1912, okay, when the Titanic shipwreck occurs, because Titanic ship is completely a welded structure, okay, which is made of carbon steel. Okay, so it is very ductile. Okay, carbon steel. So when you are sailing in a okay, when you hit a iceberg, okay, it breaks into two. So nobody understand how this ductile material behave like a brittle material. It is only in 1950s these kind of electron microscopes are invented. People begin to observe the fracture surface, and they understand that it is the ductile to brittle of transition which occurs because of very high strain rate, or when the surface reaches a sub-zero temperature and all. Okay, so next is the crystal structure. Generally it will be done using X-ray diffraction or neutron diffraction or electron diffraction. So so X-ray wavelength should be same order of magnitude as spacing between the atoms. Okay, and so suppose, see, previously, okay, so the definition of crystal is a material which possesses rotational symmetry and a translatory symmetry, but that definition people do not take it anymore. Okay, so now what they say, anything which gives a, when you subject it to a X-ray diffraction, anything which gives a sharp diffraction pattern is a crystal, and amorphous, which will give a broad peak. Okay, means the sharp peak is each peak is from a particular H scale plane, and it means that there is a regular arrangement of atom. Okay, so and the electron structures. Okay, so means you can look into inside of the atoms. Okay, or the nuclear structure. Okay, the inside structure of nucleus, like neutrons and proton presence. It can be done using nuclear magnetic resonance or Moser-Baer spectroscopes and all. Okay. And as I told you, so the main difference between scanning electron microscopes and transmission is the resolution. In a scanning electron microscope, you can resolve to the extent of tens of Armstrong. In a transmission electron microscope, less than 10 Armstrong you can resolve. Okay, so if you look into how these microscopes work, so when the incident electron beams falls on the sample, there will be interaction with the molecules or atoms, and then these interaction will lead to a secondary electrons, okay, which will give you the topographical feature or backscattered electrons, okay, or the characteristic X-rays, okay, which will provide you the information about the composition. Okay, so these are the things you can get from these kind of electron microscope, like morphology, that is the size, shape, and distribution of phases and their relation to one another. Okay, or the crystallography, that is the arrangement of atom and their degrees of order, or the detection of equilibrium and metastable precipitates, orientation relationships, and all. Okay, so and composition, okay, that is the element present in the sample and their local variation and all. Okay, and in transmission electron microscope, okay, so here okay, in the scanning electron microscope, there will be they will get scattered many times until it effectively come to rest. The means the primary electrons. Okay, but in TM, so the electron scattering scattered once or not at all when passes through the very thin samples. So here you will get a magnified image and the diffraction patterns. So when these electron being passed through, okay, a thin sample, there may be elastic scattering. So elastically scattered electrons are the main contributors to diffraction patterns. Okay, means there is no change in the energy of the primary electron detectably. Okay, there will be a Coulombic interaction. Okay, that is the electrostatic charges between the primary electrons and the nuclei and electron around it. Okay, so there will be a change in the direction. Inelastic scattering, so the primary electron loses a detectable amount of energy. Almost all the kinetic energy will end up as a heat in the sample, and small portion may escape as X-rays, okay, or the secondary electrons and all. Okay, so next is the residual stress. So the measuring or understanding the residual stress in the coating is very important. Okay, so these are the stresses which persist in the absence of external forces. Okay, which are internal, and therefore they have to be looked in, and they are contained in the material that are produced by nearly every mechanical or a chemical or thermal processes, either alone or in combination. Okay, they may be compressive or compressive stresses in coating are more favorable than the tensile stress because they increase the resistance to fatigue failure. But extremely high compressive stress, it may cause either coating separation from the base metal or intra-coating spallation. Okay, and if the tensile stress exceeds, it may cause the cracking. So the first figure is due to the excessive tensile strength. Tensile stresses, there will be a cracking in the coating, and due to the excessive compressive stress, there will be a delamination in the coating. Okay, so the origin of these residual stresses in a coating will be a combination of intrinsic stress and the thermal stress, okay, acting in the coating plane parallel to the coating substrate interface. Means at a high temperature, okay, this thermal stress arises because of the difference in the coefficient of thermal expansion between the coating and the substrate. And the intrinsic stress, they are results from the growth process. It depends primarily on deposition parameters like incorporation of residual gas atoms in the coating, grain size or microwide and dislocation density in the coating, or the energetic particle bombardment during the coating growth, or lattice misfit between the substrate and the coating, growing coating. Okay. This is just how the residual stresses, okay, develop in a HVF coating. I have taken one process just to show how the coatings originate. Okay, so in HVF coating, so the residual stresses may be due to the quenching stresses, which are tensile in nature. Okay, or it may be thermal mismatch stresses. Okay, which are tensile in nature, and the peening stress, which are a result of the grit blasting during the process. Okay, to create the rough surfaces. Okay, so they will okay, impose a compressive stresses. Okay, when you combine these quenching stress, thermal stress, and peening stresses. Okay, so you can see. So the stresses will be compressive near the interface, coating substrate interface, and if you go on increasing the thickness, so it will lead to a rise in the tensile stresses. That's why generally in HUF, so the thickness will be between 300 to 500 microns, and these residual stresses can be evaluated in using different techniques. One way is by X-ray diffraction. So it is, so in this process you can measure the stresses near surface of volume of material. Okay, and it is non-destructive in nature. Okay, so and it's based on the Bragg's law. Okay, see when a polycrystalline material is deformed elastically, okay, there will be a strain. Okay, and so the lattice plane spaces in the grain get changed from the stress-free value to a new value, which will be proportional to the applied stress, and this new spacing being constant from one grain to the other for a particular set of plane, which are similarly oriented with respect to the stresses, and this will cause the shift in the diffraction line to a new 2 theta position. Okay, and when material is deformed plastically, so when it is deformed to a new 2 theta position, so from this line shift you can calculate the strain, and from that you can calculate the stress. So maybe in different ways. One is by knowing the Young's modulus you can calculate, or by the calibration procedure, which involves the measurement of strain proportional to the stress. Okay, and when the material is deformed plastically, so the lattice plane will get distorted, and spacing of any particular H-scale plane, which will vary from one grain to the another, and this will cause a broadening of the corresponding diffraction pattern. Okay, so this is one result which we measure the residual stress, and neutron diffraction. Okay, so generally it is used to measure the stresses in large component. Neutron fluxes are much lower than the X-rays, and but the reactor used to generate the neutrons are scarce. Okay, and you can use the deflection method. Okay, so it involves measuring the amount of bend in a strip that is due to the deposition of the coating, generally in the thin films. Okay, so this deflection you can measure using various techniques like optical or capacitance or mechanical electromagnetical or interferometric or electrochemical or magnetic restoration. Okay, so maybe in your design lab and all you might have measured these using a you have measured this deflection. Okay, so the deflection is equal to the wavelength of the monochromatic light multiplied by the number of light fringes. The fringe method you might have used. Okay, and next is by hole drilling method. So the measurement of the residual stress of the coating by hole drilling method. Okay, so it is basically a destructive kind of testing. Okay, so here the residually stressed object, it is removed by cutting or any other method, and this removal will upset the pre-existing balance of forces. Okay, so the object mechanically strained, they get relaxed completely. If this strain is measured, okay, the stress originally existing can be computed. Okay, so they generally you can see here, you can drill a hole to the depth which is equal to the diameter of the drill bit, and you can mount the strain gauges. Okay, so around it. Okay, so so with this change in the when they get relaxed mechanically, so you can measure the strain. Okay, so in the similar way to the hole drilling method, you can place the strain gauge on the top of the surface, and you can we call it as a modified layer removal method. Okay, so you can determine the true thickness residual stress distribution in the coating. Okay, so the procedure involves gluing a strain gauge to the uncoated side of the spring, and then measuring the strain change after removing successive layers by mechanical polishing. Next is by nano indentation technique. Okay, so it is based on the depth, okay, of indentation. So when you indent it, so that you can measure the depth of indentation proportional to the indentation load. Okay, so once you know the load versus displacement curve, you can convert into a stress versus strain. Once you know the stress versus strain, you can measure all the bulk properties. Okay, so like Young's modulus, yield strength, strain hardening exponent, tensile strength, and along with that you can even measure the nano hardness. Okay, so so the most common means of applying the load is through electromagnetic or a piezoelectric device, in which the resolution obtained is often better than 0.1 micronewton, and displacements are typically measured by capacitive device, which gives a resolution as small as 0.1 nanometer. And I can measure the residual stress through this technique by knowing the ratio of the projected contact area. Okay, means suppose if the tensile stresses are present, it is easy for the indenter to pass through it. And suppose if the compressive stresses are present on the surface, which will resist the indentation. Okay, so based on this, so you can measure the residual stress. Okay, and the fracture toughness also. We can measure the fracture toughness by Vickers hardness indentation. Okay, we can indent in such a way that indenter diagonal will be parallel to the interface. Okay, and it will give a crack by measuring these cracks. Okay, see, this is one of our coating. We have indented and we have measured the cracks. Okay, so by knowing the Young's modulus and hardness, we can calculate the fracture toughness using these formulas. Okay, next is the Bond-Stern test. Bond-Stern test is much more important in coating. So it can be done using a direct pull-off method. Okay, you can so the coated sample is glued to the uncoated similar counterpart, that is just grid blasted and then tested in tensile in an universal testing machine. So the value of the tensile load in which the separation of the coated and uncoated part occurs is registered. Okay, and the bond strength is calculated by load versus area relation. Okay, so the failure may occur in the glue. Okay, we call it as a pour test. And the failure occurs in the bond coat or the substrate interface. We call it as an adhesive failure. Or if the failure occurs in inside the coating, we call it as a cohesive failure. Okay, so this is how the test will be conducted, and this is how the sample look like after the test. These are some of our samples which we done the bond strength test. Okay, or you can use the scratch test to measure the bond strength. Okay, you can scratch at a particular rate of loading as well as the speed. Okay, and you can along with that there will be a acoustic emission. Okay, so once the stylus reaches the substrate, which will tells you about the critical load. Okay, or the peeling test or the blister test, which will be used in a polymer kind of coatings. Okay, so these are all the various characterization we generally we have to analyze using once the coatings are developed. So I just want to show a few of our results. Okay, so the first one is elevated temperature adhesive wear behavior of microwave fused thermal spray triballoy composite coatings. So we have taken a triballoy, which is alloy of cobalt, molybdenum, chromium, silicon. We have reinforced with some of the carbides and carbides. So it is a kind of composite coating we have developed. Okay, using a HUF method. Okay, so and before HUF method, we also ball mill this triballoy to maximize the amount of leaves phases in the coating. Okay, so this is how the ball mill the powder look like. Okay, and this is the phase analysis of ball milled powder, where when you go on increasing the amount of ball milling or the duration, so it is converting from crystalline to a amorphous phase. Okay, so after that, once you achieve the amorphous phase, it is coated onto the surface using a HUF method. Okay, and then we subject it to a microwave fusing. So in this microwave fusing, we have carried out this microwave fusing using a domestic microwave oven. Okay, so the coatings are placed in a refractory brick. Okay, and above that we will place a graphite sheet which we use as a separator. Okay, and we use silicon carbide as a susceptor. Okay, which is placed above the graphite sheet, and then we have heated. Okay, so it get completely homogenized. Okay, so this is the comparison. So this is the microstructure before micro fusing, and so this is the microstructure of homogeneous structure due to a micro fusing, and this is the surface and this is the cross section. You can see the cross section; it is completely homogenized. Okay, and at the interface you can see the diffused region. Okay, and and when we look into the properties, okay, so you can see with the microwave fusing, so the porosity is reduced to a larger extent. Okay, so it is reduced to almost to the extent of more than 50%. Okay, and you can see the average micro hardness also with the microwave fusion. So the percentage increase in the micro hardness after fusion will be around 26%. Okay, so there will be a larger increment of micro hardness value as well as the porosity. Okay, so and adhesion strength, if you look into the adhesion strength of a microfused when compared to the HUF sprayed coatings, okay, so there will be improvement of around 30%, okay, increase of the adhesion strength after the fusing. Okay, so this itself say how the post coating treatment plays a role in coating deposition. So we have conducted the wear test also. So in the because of this homogeneous structure, so the microfused coatings work better than the sprayed coatings. And we have introduced a fly ash into the similar coatings along with a solid lubricants. So the fly ash, they are the sinosphere. So they are hollow spheres. Okay. So we have used this in the composition, and we also mixed the solid lubricants. Okay, as, we use solid lubricant as coating material. So these solid lubricants are transition metal disulfides, okay, are the soft noble metals like Au or Ag, or the inorganic fluorides like CF2, BF2, and metal oxides and all. Okay, and they exhibit better lubricant effect because of the lamellar or a layered crystal structure. Okay, okay. So, so this is how the composition is designed. Okay, using a solid lubricant as well as the sinosphere, and we have coated those using a plasma spraying. Okay, so you can see the presence of sinosphere as a hollow spheres in the coating composition. Okay, and so it provide a very low friction and wear rate, because you can see once we see the worn surface, so these hollow spheres, they will get opened up and collected all the particle and avoid the three body abrasion. Okay, that is the reason how the surface will be resistant to the wear, along with the formation of the oxide due to the heat. Okay, so what happened during the wear is, so this solid lubricant, it will form a lubricant film, as well as once this sinosphere opened up. Okay, so they will collect all the particle and avoid the three body abrasion. Okay, so and so one more work I want to show, that is the role of partially oxidized plasma spray nickel based coating in improving resistance to high temperature wear. So we developed this partially oxidized coating. So we have used the plasma spray process to coat the powder, means to spray the powder onto the tub of water. So when we sprayed onto the tub of water, it will get oxidized on the surface, and the core will be metallic. So then it will be dried and then milled. Okay, then we will coat those partially oxidized powder onto the surface using a plasma spray process. And when you look into these, these are the aspirate powders, and when they are partially oxidized, you can see here. So this is the image how they get oxidized on the surface, and the core is metallic. Okay, so which will provide the better toughness as well as better hardness on the surface. Okay, so and this is how the cross section looked like after the coating. Okay, which is deposited using a plasma spray technique. Okay, and when you look into the VA studies, so at different temperatures like 200, 400, and 600 degree, so these partially oxidized coating work very well than the substrate, as well as NICRB SIFE coating exhibited very high wear resistance. Okay, So this is all about a few of the studies which I have done. Any questions we can answer. I am able. I will try to clarify your doubts. Any questions?
Dear participants, if you have any queries, you can put it in the chat box or you can directly unmute yourself and speak to the speaker. Any queries? So if there is no queries, we'll end the session. Sir, thank you very much for your valuable time. We are very grateful for the time and effort you took to share your experience and thoughts with us. Your comments were very especially helpful to those who are doing research work. So we would like to have constant communication and in touch with you. Thank you very much, sir.
Okay, sir. Thank you. Thanks a lot. I will leave the meeting. Yeah.
Sure, sir. Thank you. Thank you. So feedback link will be shared in the chat box and also it will be shared in the WhatsApp group. And dear participants, tomorrow we'll be meeting exactly at 9:30 for day 2 session 1. Thank you. Have a good day.